There is a question we sometimes ask when the night is quiet and the sky above us seems impossibly deep. We ask whether everything we see, the stars, the galaxies, the faint glow of distant light, is all there is. We ask whether our universe, vast as it appears, might be only one among many. We ask whether the word universe still means what we thought it meant. You don't need to answer this question tonight. You don't need to remember what comes next. You are here to rest, to let your thoughts slow down, to allow the world to soften at its edges. If you drift away, that's fine. If you return, that's fine too. There is no test waiting. There is no conclusion you must reach. Tonight, we're going to walk slowly through an idea that lives at the boundary between what we know and what we imagine. It's called the multiverse, and it's not one idea, really. It's a family of ideas, a collection of possibilities, a set of questions that scientists have been asking carefully for decades. Let's begin gently. When we say the word universe, we usually mean everything, all of space, all of time, all of matter and energy and light, everything that exists contained in one vast cosmic structure. That's what the word has meant traditionally, the totality of what is real. But in modern cosmology, the science of the cosmos as a whole, the meaning has shifted slightly. The universe, as scientists often use the term today, refers to our observable region, the part of reality we can, in principle, detect, the part from which light has had time to reach us since the beginning. This observable region is enormous. It extends roughly 46 billion light-years in every direction from where we stand. That's the current estimate. 46 billion light-years, a distance so large that it becomes abstract, almost meaningless in everyday terms. And yet this region, vast as it is still finite. It has an edge, not a physical edge, but an observational one. Beyond that edge, light hasn't reached us yet. Beyond that edge, we simply cannot see. So when cosmologists talk about the universe, they often mean this: our observable cosmic region, the part we can study, the part we can measure, the part that is, in some sense, ours. That's one meaning of the word. Let it settle. Let it rest in your mind without effort. Now, the multiverse is something different. The multiverse is the idea that physical reality extends beyond our observable region, that there might be other regions, other domains, perhaps even other cosmic structures existing elsewhere, existing in ways we cannot directly see. These other regions might obey the same physical laws we observe here, or they might not. They might have the same fundamental constants, the strengths of forces, the masses of particles, or those constants might differ. The multiverse, in this sense, is a larger reality, a reality that contains many such domains, many such universes, if you will. It's not a single hypothesis. That's important. The multiverse is not one clear specific proposal. It's a family of scenarios, a collection of theoretical possibilities. Some of these possibilities arise from cosmology. Some arise from quantum mechanics. Some arise from string theory. They are related, but they are not the same, and they are speculative. That word matters too. Speculative. These ideas are partially motivated by existing theories, theories that have been tested, theories that work. But the multiverse itself, in most of its forms, is not something we have observed. Not yet. Perhaps not ever. Let that distinction breathe for a moment. Let it exist without judgment. The central tension here, the question that runs beneath all of this, is about the nature of science itself. It's about what counts as science and what counts as speculation. It's about how far we can extend a successful theory beyond what we can see before we lose our footing, before we step into something that cannot be tested, cannot be confirmed, cannot be touched by evidence. This is not a new tension, it's an old one. Scientists and philosophers have asked this question for centuries. When does a theory remain scientific, and when does it become metaphysics? When does extending our understanding into the unknown remain legitimate, and when does it become untestable conjecture? The multiverse sits somewhere in this uncertain space. It arises inside mainstream frameworks. That's worth emphasizing. Multiverse talk doesn't come only from science fiction, though science fiction loves it. It comes from inflationary cosmology, which is part of our standard picture of the early universe. It comes from quantum mechanics, which is one of the most successful theories ever developed. It comes from string theory, a leading candidate for a theory of quantum gravity. So these are serious ideas emerging from serious physics, and yet they remain beyond our current ability to test directly. They remain for now in that liminal space between well-established science and something more speculative. You don't need to resolve this tension. You don't need to decide where the boundary lies. You can let it remain unresolved. Let it remain a question, drifting in the stillness of the night. The debate itself is active. Leading cosmologists discuss these ideas. Philosophers of science write papers about them. Some argue that multiverse scenarios are scientifically meaningful, even if we cannot visit other universes, even if we cannot measure them directly. They argue that these scenarios emerge as consequences of theories we trust, theories that make other predictions we can test. Others argue the opposite. They say that postulating entities we can never observe, regions we can never reach, is a step too far. They say it weakens the traditional requirement that scientific claims must be falsifiable, must be checkable against evidence. They worry that multiverse arguments rely too heavily on something called anthropic reasoning, an idea we'll encounter later, and that this reasoning is circular, unsatisfying, perhaps even unscientific. Both positions are held by serious, thoughtful people. Both have merit, and neither has won the debate. Let that uncertainty settle. Let it be okay that we don't have an answer yet. In modern cosmology, when we speak of the universe, we mean something specific and limited. We mean the region of space and time from which light has been able to reach us. We mean the observable universe, its size, that 46 billion light-year radius is determined by two things: the speed of light, which is finite, and the age of the cosmos, which is also finite. Light travels fast, but not infinitely fast. The universe has existed for a long time, but not forever. These two limits combine to give us a horizon, a boundary of visibility. Beyond that horizon, there may be more space, more galaxies, more stars, more structure, or there may not be. We don't know. We can't see it yet. We may never see it. And the multiverse, the idea, the family of ideas, proposes that reality extends beyond even this, that there are regions, perhaps infinitely many regions, with different initial conditions, with different histories, with different physical parameters, possibly even different effective laws. This is not a single hypothesis. Let me say that again, slowly. The multiverse is not one thing. It is many proposals, many scenarios, many levels of speculation. Some are more closely tied to tested physics than others. Some are more radical. Some are widely discussed. Some are regarded with deep skepticism. But they all share this. They suggest that what we see is not all there is. Breathe for a moment. Let your mind rest. You don't need to understand everything. You don't need to hold all of this at once. The ideas can drift through your awareness like clouds, like shadows, like distant lights in the dark. We're going to move slowly through these ideas. Now, we're going to explore them one by one, gently, without rushing. We're going to see where they come from and what they propose. We're going to ask what we can test and what we cannot. And we're going to live comfortably with the fact that many questions remain unanswered. That's the nature of the frontier. The edge of knowledge is always uncertain. It's always hazy, and that's okay. Let the uncertainty be part of the calm. There is a way of organizing these multiverse ideas that has become influential in cosmology. It was proposed by a physicist named Max Tegmark. He divided multiverse proposals into 4 levels, 4 distinct categories, each based on different pieces of physics, each conceptually different from the others. These levels are not stages of a single theory. They don't build on one another in a simple way. They are parallel possibilities, different ways that reality might be larger than we see. Level 1 is the simplest. It's the idea that space extends far beyond our observable horizon, that if you could travel far enough, farther than light has travelled in the age of the universe, you would find more galaxies, more stars, more planets, the same laws of physics, the same fundamental constants, but different initial conditions, different arrangements of matter, different histories. This level arises naturally if space is, as many inflationary models suggest, statistically uniform at large scales. If the universe is in some sense the same everywhere, then distant regions will look like ours on average, but they will differ in detail. And if space is infinite, or even just very large, then every possible arrangement of matter, every possible history will occur somewhere, including exact duplicates of this region, exact duplicates of you. That's level 1. It's strange, but it's not as radical as the others. It doesn't require new physics. It just requires space to be big enough. Let that idea rest. Level 2 is different. Level 2 invokes eternal inflation, a scenario we'll explore more carefully later. In Level 2, different regions of space, different bubbles or pocket universes, don't just have different initial conditions, they have different low-energy physical constants, different values for the strengths of forces, different particle content, perhaps even different numbers of spatial dimensions. This level arises in some models of inflation and in some approaches to string theory. In these models, the universe undergoes a rapid expansion in its earliest moments, and this expansion never completely stops everywhere at once. Instead, it continues in some regions while ending in others, creating a patchwork of thermalized bubbles inside a still inflating background. Each bubble can settle into a different vacuum state, a different configuration of fields and symmetries, leading to different effective laws. This is more speculative than level 1. It depends on specific assumptions about the physics of the early universe and the structure of fundamental theory. But it's not science fiction. It's a serious possibility within some well-developed frameworks. Let the strangeness of that settle without resistance. Level 3 is something else entirely. Level 3 comes from quantum mechanics, from a particular interpretation of quantum mechanics, one that takes the mathematical formalism seriously and refuses to add extra postulates about measurement or collapse. It's called the Everett interpretation, or the many worlds interpretation, and the idea is this: the quantum wave function never collapses. It never jumps from a superposition to a single outcome. Instead, it evolves smoothly, unitarily, according to the Schrödinger equation. And when a measurement happens, when a system decoheres, when it interacts with its environment in a way that distinguishes different possibilities, the wave function splits into effectively non-interacting branches. Each branch corresponds to one outcome. Each branch is, in some sense, a separate world. This is not a multiverse in space. It's a multiverse in the space of quantum states, a multiverse of histories, not places, and it's deeply controversial. Not because the physics is wrong, the physics of decoherence is well studied and well understood, but because the interpretation, the ontological claim about what's really happening is disputed. Some physicists embrace it, others reject it, most remain agnostic. Let that ambiguity be present. Let it be unresolved. Level 4 is the most radical. It's the proposal that every mathematically consistent structure exists as a physical reality, that the laws of physics themselves, not just the constants, not just the initial conditions, but the fundamental equations, vary across different universes. That reality is, in some sense, the collection of all possible mathematical structures. This level is highly speculative. It's not widely adopted as a working framework. It's more of a philosophical idea, an attempt to answer the question, why these laws and not others? The answer level 4 gives is all laws, all possibilities. Everything that can be described mathematically exists. Most physicists don't take this seriously as a literal description of reality, but it's included in Tegmark's classification because it represents the logical endpoint of multiverse thinking. If you're willing to accept that there are many universes, why stop at many regions or many quantum branches? Why not many mathematical structures? You don't need to accept it. You don't even need to fully understand it, just let it exist as a possibility, distant and abstract, at the far edge of speculation. These are the 4 levels, 4 ways of thinking about the multiverse, 4 frameworks, each with its own assumptions, its own motivations, its own uncertainties. We'll explore some of them in more detail as we move forward. We'll look at where they come from. We'll look at what they predict, if anything. We'll look at whether they can be tested. But for now, just hold them lightly. Hold them as ideas, as proposals, as possibilities, not as facts, not as established truths, as questions. Breathe again. Let your body relax. The night is still around you. The universe, whatever it is still there. Vast, quiet, indifferent to our attempts to understand it. And that's okay. We are small creatures, asking large questions. We do our best. We build theories, we make measurements, we argue and debate and refine our understanding. And sometimes we reach the edge of what we can know. Sometimes we find ourselves staring into uncertainty. The multiverse is one of those edges, one of those places where our theories extend beyond our evidence, where mathematics suggests possibilities we cannot confirm, where imagination and rigor meet, and neither is quite enough. Let that be enough for now. Let's turn now towards something more concrete, something that begins with observations we trust and extends carefully into territory that is less certain. Let's talk about inflation, about the early universe, about how a successful theory, tested and confirmed in many ways, might lead us almost inevitably toward the idea of multiple universes. You can rest as we walk through this. You can let the details wash over you. The important thing is not to memorize, not to master, but simply to follow along gently as one idea leads to another. Inflation is part of our standard picture of cosmology now. It's the idea that the universe, in its earliest moments, a tiny fraction of a second after the beginning, underwent a period of extraordinarily rapid expansion, faster than anything we see today, faster, in a sense, than the speed of light, though that's not quite the right way to say it. Space itself expanded. The fabric of the cosmos stretched exponentially, doubling in size again and again in incomprehensibly brief intervals. This proposal was introduced decades ago to solve certain puzzles about the observable universe, puzzles about why space appears so flat, why distant regions that should never have been in contact look so similar, why the universe is so homogeneous, so uniform on the largest scales. Inflation solves these puzzles elegantly. If the universe inflated, if it expanded enormously in those first moments, then regions that are now far apart were once close together. They could have reached the same temperature, the same density, before being pulled apart by expansion. And the stretching itself would flatten space, smooth out irregularities, explain the patterns we see. This is not speculation, not anymore. Inflation makes predictions about the spectrum of fluctuations we should observe in the cosmic microwave background, the faint glow of radiation left over from the early universe, and those predictions match the data beautifully, precisely. The measurements from satellites observing this ancient light support the inflationary picture. They support the idea that something like this happened. So inflation is part of our standard cosmological paradigm. It's a successful theory, a tested framework. But inflation, it turns out, has implications. Implications that extend beyond what we've confirmed. Implications that lead, in many models, towards something called eternal inflation. Let that thought begin to form slowly. Here is what happens in many inflation models, perhaps most of them. The field that drives inflation, a hypothetical scalar field, often called the inflaton, is subject to quantum fluctuations, tiny random variations in its value from place to place. In most regions, the field rolls down toward lower energy, and inflation ends. The universe transitions into a hot, dense state, a state of ordinary matter and radiation. That's what happened in our observable region. But in some regions, because of these quantum fluctuations, the field gets kicked back up. It climbs to higher energy instead of lower. And in those regions, inflation doesn't end. It continues. And as it continues, space keeps expanding, keeps creating new volume. And in that new volume, quantum fluctuations occur again. Some regions end their inflation, others don't. This process repeats. It feeds on itself. Regions that keep inflating produce more space, which produces more regions, some of which keep inflating, which produces more space. It's self-reproducing. It's eternal, not in the sense that it has no beginning, but in the sense that once it starts, it never completely stops. Somewhere, always, inflation is still happening. This is called eternal inflation. And if eternal inflation is real, if this is how inflation actually works, then our observable universe is just one bubble, one thermalized region, one pocket where inflation ended and matter formed, among infinitely many such pockets. Let that idea settle. Let it expand in your mind the way space itself expands in the theory. Each bubble, each pocket universe, exists inside a larger inflating background. The bubbles are separated by regions that are still inflating, still stretching, still growing, and because the expansion is so rapid, the distance between bubbles increases faster than light can cross it. They are causally disconnected, permanently. We cannot see other bubbles, we cannot visit them, we cannot signal to them. They exist, if they exist at all, in a part of reality that is forever beyond our horizon. This is the level a multiverse in its simplest form. Different regions, same laws, different initial conditions, but eternal inflation can go further. It can lead to a level 2 multiverse, where the bubbles differ not just in their arrangements of matter, but in their physical constants, in their effective laws. How does that happen? How can the laws of physics vary from place to place? The answer involves something called vacuum states, something called symmetry breaking, concepts from quantum field theory, and in some versions from string theory. Let it unfold slowly. In fundamental physics, what we call the laws of nature are often not absolute. They are low-energy descriptions of something deeper. At very high energies far beyond what we can produce in our laboratories, the universe may have more symmetry, more possibilities, more freedom. But as the universe cools, as energy decreases, those symmetries can break. The system settles into one particular configuration, one particular vacuum state, out of many possible ones. And different vacuum states can lead to different low-energy physics, different values for the masses of particles, different strengths for the fundamental forces, different numbers of effective dimensions. String theory, a framework that attempts to unify quantum mechanics and gravity, suggests that there are many such vacuum states, enormously many, perhaps 10 to the 500, perhaps more. This collection of possibilities is sometimes called the landscape, the string landscape, a vast space of potential universes, each with its own set of low-energy parameters. Now combine this with eternal inflation. If inflation creates infinitely many bubble universes, and if different bubbles can settle into different vacuum states from the landscape, then the result is a level 2 multiverse, a multiverse in which the fundamental constants vary, in which the physics itself at the level we experience it differs from place to place. This is highly speculative. String theory itself is not yet empirically confirmed. The landscape is a theoretical construct, not an observed fact. And the idea that different bubbles realize different vacua is an extrapolation, not a prediction we can test directly. But it's not arbitrary, it's not science fiction. It arises from serious attempts to understand the early universe and the nature of fundamental theory. It's an implication, a possibility, a scenario that some of our best frameworks suggest. Let the speculative nature of this be present. Let it be acknowledged without anxiety. There is a problem here, a technical problem that cosmologists who work on these ideas take very seriously. It's called the measure problem. If the multiverse is eternal, if inflation produces infinitely many regions, then how do we assign probabilities to different observations? How do we predict what a typical observer should see? In a finite universe, this is straightforward. You count the observers, you count the outcomes, you calculate frequencies. But in an infinite multiverse, every possible outcome occurs infinitely many times. There are infinitely many observers like you seeing what you see, and infinitely many seeing something else, and infinitely many seeing something else still. Infinity minus infinity is not well defined. Infinity divided by infinity is not well defined. The usual rules of probability break down. Different proposals for how to handle this, different measures, give different answers, different predictions, and there is no consensus about which measure is correct, or even whether the question has a unique answer. This is an open problem, a serious one. It doesn't invalidate the multiverse idea, but it limits our ability to use it to make predictions. It leaves the framework incomplete. Let that incompleteness exist. Let it be part of the picture. Breathe for a moment. Let your thoughts drift. We've been talking about cosmic bubbles, about regions of space inflating and thermalizing, about vacuum states and landscapes. These are abstract ideas, mathematical structures, theoretical possibilities. They are far from everyday experience, far from anything we can see or touch, and that's okay. Science often works at this level. It often extends beyond the tangible. The question is whether it extends too far, whether it loses its grounding, whether it becomes something other than science. We'll return to that question, but not yet. For now, just rest in the strangeness of it all. The possibility that our universe is one, bubble among many. The possibility that the constants we take for granted, the ones that make atoms stable, that allow stars to shine, that permit life to exist, might be different elsewhere, might be in some sense accidental, local, not fundamental truths, but contingent facts. Let that idea be uncomfortable if it needs to be. Let it be unsettling, or let it be fascinating, or let it be nothing at all. Just words in the dark, just sounds that fade into stillness. The connection between eternal inflation and the string landscape is sometimes used to address a very old question. A question that has puzzled scientists and philosophers for a long time. The question is this: why are the constants of nature what they are? Why does the electron have the mass it has? Why is the cosmological constant, the energy of empty space, so small? Why is the strength of gravity so weak compared to the other forces? These values seem fine-tuned, delicately balanced. If they were even slightly different, stars wouldn't form, chemistry wouldn't work, life, at least as we know it, couldn't exist. This fine-tuning is striking. It's not proof of anything, but it's puzzling. And one way to address the puzzle is through something called anthropic reasoning combined with a multiverse. The argument goes like this: if there are many universes, many bubbles, each with different constants, then most of them will be inhospitable. Most will not form complex structures. Most will not harbour life. But some will. And the only universes in which observers can exist, the only ones in which anyone can ask the question, why these constants, are the ones where the constants allow for observers. So the fact that we find ourselves in a universe with life-friendly constants is not surprising. It's a selection effect. we couldn't be anywhere else. We couldn't observe any other kind of universe because we wouldn't exist in those universes. This is anthropic reasoning. And it's controversial. Let that controversy breathe. Some physicists find anthropic reasoning compelling. They say it's no different from any other selection effect in science. If you're trying to understand why Earth has liquid water, part of the answer is that we live on Earth. We wouldn't be here asking the question if the conditions weren't right. The multiverse, combined with anthropic reasoning, offers a similar explanation for cosmic fine-tuning. Others find it deeply unsatisfying. They say it's not really an explanation at all. It doesn't tell us why the constants have the values they do in our universe. It just says that other values exist elsewhere, and we happen to be here. It shifts the mystery rather than solving it, and it seems unfalsifiable. How can we test the claim that other universes exist if we can never observe them? Both positions are held by thoughtful people, both have merit, and the debate is not resolved. Let the unresolved nature of this sit quietly in your mind. The string landscape, the idea that there are many possible vacuum states, is itself uncertain. String theory has not yet been confirmed experimentally. Makes predictions at energy scales far beyond what our accelerators can reach. And even within string theory, there is no universally accepted mechanism for selecting which vacuum we live in, or for deriving the distribution of vacua that eternal inflation might populate. So the landscape is a theoretical construct, a possibility, a framework that might be right or might not be. And the combination of the landscape with eternal inflation is even more speculative. It depends on both frameworks being correct. It depends on inflation being eternal. It depends on different bubbles realizing different vacua. It depends on a chain of assumptions, each individually uncertain, compounding into something that is far from established fact. This doesn't mean it's wrong. It means it's at the frontier. It means we don't know yet. Let that uncertainty be acceptable. In some cosmological scenarios, in some versions of eternal inflation combined with the string landscape, different inflationary bubbles settle into different vacuum states. Each bubble becomes a pocket universe with its own low-energy physics, its own values for fundamental constants, its own particle spectrum, its own effective dimensionality, if extra dimensions are compactified in different ways. This leads to a level 2 multiverse, a multiverse where the physics itself varies, where the rules we observe here are not universal but local, where the constants we measure are not fundamental but environmental. It's a radical idea. It changes how we think about the nature of physical law. It suggests that what we've been trying to explain, the specific values of constants, might not have a unique explanation, might not have a deep reason, might just be a matter of where we happen to find ourselves in a vast landscape of possibilities. Some find this liberating, others find it troubling. It depends perhaps on what you were hoping physics would tell you, whether you were hoping for uniqueness or for diversity, for necessity or for contingency. Let both feelings coexist. These ideas, eternal inflation, the string landscape, anthropic reasoning, are serious topics in contemporary cosmology. They appear in peer-reviewed papers, they are discussed at conferences, they are debated by leading researchers, but they are not confirmed. They are not part of the established body of scientific knowledge in the same way that, say, general relativity or quantum mechanics are. They are proposals, possibilities, scenarios that might be true, and they are controversial because they push at the boundaries of what we can test, because they involve entities, other universes, other vacua that may be forever beyond our observational reach, because they seem to challenge the traditional criteria of scientific inquiry, but they arise from theories we trust. They emerge as implications of frameworks that have been successful in other contexts, and that's why they're taken seriously, even as they remain uncertain. Let that tension, the tension between taking them seriously and remaining skeptical, be part of the landscape you're resting in tonight. Breathe deeply. Let your shoulders soften. Let the weight of these ideas disperse into the air around you. We've been talking about cosmic structures, about space and time and bubbles, about fields and vacua and constants. But there is another kind of multiverse, another way that reality might be larger than what we see. And it comes from a completely different place. It comes from quantum mechanics. Let's turn toward that now, slowly, without hurry. Quantum mechanics is strange. That's not a controversial statement. Everyone who works with quantum theory acknowledges its strangeness, its departure from everyday intuition, its refusal to behave the way we expect the world to behave. And at the heart of this strangeness is something called the measurement problem, a puzzle that has persisted for nearly a century, a question about what happens when we observe a quantum system, when we measure it, when we interact with it in a way that produces a definite outcome. You don't need to solve this problem tonight. Physicists haven't solved it either, not fully, but we can walk through it together, gently, and see where it leads. In quantum mechanics, systems exist in superpositions. That's the technical term. A superposition is a state in which multiple possibilities coexist simultaneously, not because we don't know which one is real, but because, in a deep sense, they're all real at once. They're all part of the quantum state. An electron can be in a superposition of spinning up and spinning down. A particle can be in a superposition of being here and being there. A quantum system, before it's measured, exists in this ambiguous, multifaceted condition. The mathematics describes this beautifully. It's precise. It's unambiguous. The wave function, the mathematical object that encodes the quantum state, evolves according to an equation called the Schrödinger equation. And the Schrödinger equation is deterministic. Given the wave function at one time, you can calculate it at any other time. It evolves smoothly, continuously, unitarily. But then something happens when we measure the system, when we look at it, when we interact with it in a way that registers an outcome. The superposition seems to collapse. The many possibilities reduce to one. The wave function jumps discontinuously to a state corresponding to the result we observe. This is the measurement problem. Why does this happen? How does it happen? What counts as a measurement? Where in the physical process does the collapse occur? Let these questions hang in the air, unanswered. There are many ways to respond to the measurement problem, many interpretations of quantum mechanics. Each one attempts to make sense of what's happening, to reconcile the smooth evolution of the wave function with the definite outcomes of experiments. The Copenhagen interpretation, historically the most common, says that the wave function describes our knowledge, not reality itself. When we measure, we gain information, and the wave function updates accordingly. The collapse is not a physical process, it's an epistemological one. Other interpretations propose that collapse is real, that something physical happens, that quantum mechanics is incomplete and needs to be supplemented with additional dynamics. Theories of objective collapse suggest new mechanisms, new terms in the equations that cause the wave function to spontaneously localize under certain conditions. And then there is another interpretation, one that takes a different path entirely, one that refuses to add collapse to the theory, one that says the wave function never collapses, ever. This is the Everett interpretation, the many worlds interpretation, and it leads naturally, inevitably, to a kind of multiverse. Let that idea approach slowly. The Everett interpretation starts with a simple question. What if we take the Schrödinger equation seriously? What if we don't add collapse as an extra postulate? What if the wave function just keeps evolving, smoothly, unitarily, always? If that's the case, if the wave function never collapses, then what happens during a measurement? The answer involves a process called decoherence. Decoherence is not controversial. It's a well-studied, well-understood aspect of quantum mechanics. It happens when a quantum system interacts with its environment, when a small system becomes entangled with a large, complex environment. Air molecules, photons, thermal fluctuations. The interference between different components of the superposition is suppressed. The system appears, for all practical purposes, to behave classically, to occupy a definite state. But decoherence doesn't reduce the number of possibilities. It doesn't pick one outcome over another. It just spreads the superposition into the environment. It makes the different components effectively non-interacting. They stop interfering. They stop being able to influence one another. In the Everett picture, each component continues to exist. Each branch of the wave function is real. When you measure an electron spin, the wave function doesn't collapse to up or down. Instead, it evolves into a superposition of two branches, one in which you observe up and one in which you observe down. Both branches exist. Both are real. You exist in both. Or rather, there are two versions of you, one in each branch, each experiencing a definite outcome. This is the many worlds interpretation, a quantum multiverse, not of separate spaces but of separate histories, separate branches of a universal wave function. Let the strangeness of this wash over you without resistance. Decoherence explains why we experience definite outcomes even though the wave function contains many possibilities. It explains why macroscopic objects behave classically, why we don't see tables existing in superpositions of being here and there. The environment constantly decoheres macroscopic systems, selecting certain pointer states, robust states that remain stable under interaction with the environment. This is uncontroversial physics. This is something almost all physicists agree on. What's controversial is the ontological interpretation, the claim about what's real. Everettians say that all branches are real, that decoherence creates an effective branching structure, and each branch is a world, a history, a version of reality. Other interpretations deny this. They say decoherence explains appearances, but it doesn't eliminate the need for collapse. Or they say the branches aren't real worlds, just mathematical components of a single wave function. Or they say the question of what's real isn't well defined. There is no consensus. Let the lack of consensus be peaceful. If the many worlds interpretation is correct, if all branches are real, then the universe is constantly splitting. Every time a quantum event occurs, every time a measurement happens, every time decoherence carves the wave function into distinct branches, reality multiplies. The number of worlds grows exponentially, unimaginably. And these worlds are not separate places. They're not located in different regions of space. They exist in a more abstract sense. They're different components of the quantum state. Different terms in the wave function, different histories that have decohered from one another. You cannot visit another branch. You cannot interact with it. You cannot even, in principle, detect it. The branches are causally isolated. Once decoherence has occurred, once the branches have separated, they never recombine. They never interfere again. They are effectively separate universes. This is the level 3 multiverse, a multiverse in Hilbert space. In the space of quantum states, not in physical space. It's conceptually very different from the level 1 or level 2 multiverses we discussed earlier. Those were about regions of physical space. This is about branching in quantum configuration space. Let both ideas coexist in your mind, distinct and separate. The many worlds interpretation has its defenders and its critics. Its defenders say it's the simplest interpretation. It takes the quantum formalism at face value. It doesn't add collapse. It doesn't introduce new dynamics. It just follows the Schrödinger equation wherever it leads. And where it leads is to a branching structure of histories, all equally real. Its critics raise several objections. One is the question of probability. In standard quantum mechanics, we can predict the probability of different outcomes. But if all outcomes occur in different branches, what does probability mean? Why do we experience some outcomes more frequently than others? How do we derive the Born rule, the rule that gives probabilities from the wave function within the Everettian framework? This is an active area of research. Some Everettians believe they've solved the problem, others remain unconvinced. The debate continues. Another criticism is ontological. The many worlds interpretation postulates an enormous number of unobservable entities, infinitely many branches, infinitely many versions of you, all existing simultaneously, never interacting, never detectable. Critics say this is a heavy metaphysical price to pay, that parsimony, preferring simpler explanations, should count against it. Defenders respond that the branches aren't added, they're already there in the wave function. The structure is already present in the mathematics. Everett just takes it literally. Let both arguments rest without choosing between them. Decoherence is a physical process. It happens, we can calculate it, we can observe its effects. It's the reason why quantum computers are so difficult to build. Environmental decoherence destroys the delicate superpositions we're trying to manipulate. It's the reason why macroscopic objects behave classically. It's deeply understood. But decoherence alone doesn't tell us what's real. It doesn't tell us whether the branches are separate worlds or just mathematical bookkeeping. It doesn't resolve the measurement problem, though it clarifies it. It shifts the question from why do we see one outcome to what makes one branch our experience. And different interpretations answer that second question differently. Many worlds says all branches are experienced just by different versions of you. Copenhagen says the question doesn't make sense because the wave function isn't reality. Objective collapse says only one branch becomes real through some physical mechanism. They all fit the data. They all reproduce the same experimental predictions. That's why the choice between them is interpretational, not empirical, at least not yet. Let the undecidability be part of the quietness of this moment. Some physicists argue that the many worlds interpretation is not just one option among many, but the natural consequence of taking quantum mechanics seriously. They argue that once you accept the Schrödinger equation as fundamental, once you refuse to add collapse by hand, branching follows inevitably. The wave function evolves, decoherence occurs, structure emerges, and that structure looks like separate worlds. Other physicists argue that this is too quick, that decoherence explains appearances but doesn't mandate a particular ontology, that you can accept the Schrödinger equation and decoherence without accepting that all branches are real, that the interpretation of the formalism is still open, and still others argue that quantum mechanics itself might need modification, that we might discover new physics at some scale, perhaps where quantum mechanics meets gravity, that resolves the measurement problem in a different way. That collapse might be real after all, driven by some mechanism we haven't yet identified. All of these positions are held by serious researchers, all are defended in the literature, and none has won the debate. Let the debate continue without you. Let it be background noise, distant and inconsequential to your rest. Breathe again. Let your mind wander. We've been talking about quantum mechanics, about superpositions and measurements, about decoherence and branching, about the possibility that every quantum event spawns new worlds, new histories, new versions of reality. It's abstract, it's strange, it's far from anything we experience directly, and yet quantum mechanics is the most successful theory in physics. It underlies all of chemistry, all of materials science, all of electronics. The device you're listening to this on exists because we understand quantum mechanics. The theory works spectacularly. The question is what it means, what it's telling us about reality. And that question, despite a century of debate, remains open. The multiverse that emerges from quantum mechanics, if it emerges at all, is not a multiverse of distant regions. It's a multiverse of branching possibilities, of diverging histories, of a reality that is, at its deepest level, more complex than we ever imagined. Or maybe it's not. Maybe the branches aren't real. Maybe there's a different way to understand quantum mechanics that doesn't require this vast multiplication of worlds. We don't know yet. Let that be okay. There's something worth noting here, something about the relationship between different multiverse ideas. The level 3 multiverse, the quantum multiverse, is conceptually distinct from the level 1 and level 2 multiverses we discussed earlier. Those were about cosmology, about regions of space, about eternal inflation and string vacua. This is about quantum mechanics, about the structure of quantum states, about how possibilities branch as systems decohere. But some physicists have argued that they might be connected, that in an infinite level 1 multiverse, where every possible initial condition is realized somewhere, the different branches of the quantum wave function might correspond to different regions of space. that what looks like quantum branching from one perspective might look like spatial separation from another. This is highly speculative. It's a research topic, not an established result. Some argue it's true, others argue it's confused, that it conflates distinct concepts. The question is not settled. Let it remain unsettled. The many worlds interpretation, whatever its ultimate status, represents a particular kind of response to the measurement problem. It takes the formalism seriously. It resists adding extra structure. It follows the mathematics where it leads. And where it leads is to a picture of reality that is vast, sprawling, incomprehensibly large. Every quantum event, every particle interaction, every photon absorption, every radioactive decay spawns new branches. The universe, or the wave function, or reality, or whatever we want to call it, is constantly differentiating, constantly multiplying, constantly creating new histories. Most of those histories are very similar to ours. The branches diverge slowly at first. A photon goes left instead of right. A particle decays now instead of a moment later. Tiny differences that accumulate over time. But eventually the branches can diverge significantly. Different outcomes to measurements, different sequences of events, different versions of history, and in each branch there are observers, people, versions of you, each experiencing their branch as the only reality, each unaware of the others. If the interpretation is correct, let that conditional be present always. Critics of many worlds sometimes point to the sheer extravagance of it, the ontological cost, the claim that reality contains not just the world we see, but infinitely many variations of it, infinitely many versions of every person, every moment, every choice. It seems wasteful, excessive, unparsimonious. Defenders respond that simplicity should be judged by the theory, not the ontology. The theory, just the Schrödinger equation, with no collapse, is simple. The ontology, many worlds, is complex, but that complexity emerges from the simple theory. It's not added by hand. Who's right? It depends on how you weigh simplicity, on what you think matters more, elegant theory or economical ontology. Different people make different choices. Let both perspectives exist in the stillness of the night. The measurement problem at its core is about the relationship between quantum mechanics and experience, between the formalism and what we actually observe. The math describes superpositions. We experience definite outcomes. How do we bridge that gap? Many worlds says we don't. Both are real. This superposition exists. The definite outcome exists. You just experience one branch of the superposition, and another version of you experiences another branch. Other interpretations bridge the gap differently, by adding collapse, by redefining what the wave function represents, by modifying the dynamics. Each approach has costs and benefits. Each solves some problems while creating others, and none is forced by the data. The experiments we can do don't distinguish between interpretations. They can't. The interpretations are designed to reproduce the same predictions. So the choice, for now, is philosophical, aesthetic, personal. Let it remain that way, unforced and gentle. Breathe once more. Let your body sink deeper into rest. We've travelled through quantum mechanics now, through superpositions and decoherence, through the many worlds interpretation and its critics, through the idea that reality might be branching constantly, creating new worlds with every quantum event. It's a lot to hold, and you don't need to hold it. You can let it drift away, let it dissolve into the background. What remains is simpler. Quantum mechanics is strange. The measurement problem is unsolved. Some interpretations lead to multiverses, others don't. We don't know which is correct. That's the honest summary. That's where we are. And it's okay to rest there, in that uncertainty, without needing resolution. We've been walking through different kinds of multiverses, different ways that reality might extend beyond what we see. We started with cosmic bubbles, with eternal inflation, with the idea that space might contain many regions, each with its own physical constants. Then we turned to quantum mechanics, to branching wave functions, to the possibility that every measurement creates new worlds. Now let's come back to cosmology, back to string theory, back to a particular combination of ideas that has been influential and controversial in equal measure. Let's talk about the landscape, about vacuum states, about anthropic reasoning, about how physicists have tried to explain why the universe looks the way it does. You can rest as we move through this. Let the ideas come and go like waves, like breath, like distant echoes. String theory is an attempt to unify quantum mechanics and gravity, to find a single framework that describes both the very small, particles, fields, quantum effects, and the very large, space-time, gravity, cosmology. It's one of the leading candidates for such a framework, though it's not the only one, and it's not yet confirmed. The basic idea is that fundamental entities are not point particles, but tiny vibrating strings, one-dimensional objects. The way a string vibrates determines what kind of particle it appears to be: an electron, a quark, a photon. All different vibrational modes of the same underlying string. For the mathematics to work, for the theory to be consistent, string theory requires extra dimensions, not just the 3 spatial dimensions we experience, but additional ones, 6 extra dimensions in most versions, 10 dimensions total, counting time. But we don't see these extra dimensions, we experience only 3. So string theory proposes that the extra dimensions are compactified, curled up, wrapped into tiny geometric shapes so small that we can't detect them. And here's where things get interesting. There are many ways to compactify extra dimensions, many different geometric shapes, many different configurations, and each configuration leads to different low-energy physics, different particles, different forces, different values for constants. This multiplicity of possibilities is called the landscape, the string landscape, a vast space of potential universes, each corresponding to a different way of compactifying the extra dimensions. Let that vastness settle in your mind slowly. How many possibilities are there? How large is the landscape? Estimates vary, but they're enormous. Some calculations suggest 10 to the 500 different vacuum states. That's a 1 followed by 500 zeros, a number so large it's essentially meaningless, larger than the number of particles in the observable universe, larger than anything we encounter in everyday experience, and each of these vacuum states represents a different possible universe. A different set of physical laws, at least at the level we experience them, different electron masses, different force strengths, different cosmological constants. This diversity is both a blessing and a curse. It's a blessing because it offers potential explanations for things that otherwise seem arbitrary. Why does the electron have the mass it does? Maybe there's no deep reason. Maybe it's just the value that happens to exist in the vacuum we inhabit. Other vacua have other values, but it's a curse because it removes predictive power. If string theory allows almost anything, then it predicts almost nothing. We can't derive the electron mass from first principles. We can only observe it and note that it's one of the possibilities the theory permits. This is one reason string theory has been controversial, not because it's wrong, we don't know if it's wrong, but because it might not be the kind of theory we were hoping for. Not a theory that uniquely determines the constants, but a theory that allows a vast range of possibilities. Let that disappointment, if you feel it, be present without judgment. The landscape becomes cosmologically relevant when you combine it with eternal inflation. Remember eternal inflation, the idea that quantum fluctuations keep some regions inflating while others thermalize, creating a mosaic of bubble universes in an ever-expanding background. Now add the landscape. In some models of eternal inflation, different bubbles can settle into different vacuum states from the string landscape. As each region stops inflating, it undergoes a phase transition. The extra dimensions compactify, the symmetries break, and the system falls into one of the many possible vacua. Different bubbles fall into different vacua, and because there are so many vacua and so many bubbles, every possibility is realized somewhere. Every vacuum state, every set of constants, every configuration of the extra dimensions exists in some bubble universe. This is the level 2 multiverse again, but now grounded in a specific theoretical framework. String theory plus eternal inflation equals a vast multiverse of bubble universes with different physical laws, or so the argument goes. Let it rest there, neither accepted nor rejected. None of this is confirmed. That needs to be said clearly. String theory is not an experimentally verified framework. We have no direct evidence for extra dimensions for strings, for the compactifications the theory proposes. The mathematics is elegant, the ideas are compelling to many physicists, but the connection to observation remains tenuous, and eternal inflation, while motivated by successful inflationary cosmology, is also not directly confirmed. We've seen evidence that inflation happened. We haven't seen evidence that it's eternal. We haven't detected bubble collisions. We haven't measured signatures of different vacuum states. So the combination, string landscape plus eternal inflation, is speculative. It's a scenario that might be true, a possibility worth exploring, but it's not established fact. It's important to hold that distinction, to know where the confirmed science ends and where the theoretical extrapolation begins. Let that boundary be clear, even if it's fuzzy. The string landscape is used in arguments about fine-tuning, about why the constants of nature have the values they do, particularly about the cosmological constant, which is one of the most puzzling values in all of physics. The cosmological constant measures the energy of empty space. According to quantum field theory, empty space shouldn't be empty. Virtual particles should appear and disappear, contributing energy, and when you calculate how much energy, you get an answer that's huge, enormous, many orders of magnitude larger than what we observe. But observations show that the cosmological constant is tiny, not zero, but incredibly small. Small enough that the universe expands slowly, gracefully, allowing galaxies to form, stars to shine, life to emerge. If the cosmological constant were much larger, the universe would have expanded too rapidly. Structure wouldn't form. Galaxies wouldn't exist. We wouldn't be here to ask the question. This is the cosmological constant problem. Why is it so small? Why is it small enough to allow for life but not exactly zero? Without a multiverse, this seems like an incredible coincidence, a mystery, a fine-tuning that demands explanation. With a multiverse, with a landscape of vacua, each with different values for the cosmological constant, the answer becomes anthropic. Most vacua have large cosmological constants. Most are inhospitable, but some have small values, and we find ourselves in one of those because we couldn't exist in the others. It's a selection effect, not a deep explanation, but a constraint on where observers can be. Let that explanation sit with you. Let it be unsatisfying if it feels unsatisfying. Anthropic reasoning is controversial. Some physicists embrace it as a legitimate form of scientific explanation. They point out that selection effects are common in science. If you're studying stars, you're biased towards stars that shine long enough for you to evolve and look up. If you're studying planets, you're biased toward planets that can support life. Anthropic reasoning about the multiverse is just an extension of this logic. Other physicists reject it. They say it's giving up, that we should be looking for a deeper explanation, a mechanism that determines the cosmological constant uniquely rather than appealing to a vast ensemble of possibilities and saying we're lucky to be in one of the good ones. They worry that anthropic reasoning is unfalsifiable, that it can explain anything. If the constants were different, we'd just say we're in a different bubble. It doesn't predict. It doesn't constrain. It just accommodates. Both critiques have force. Both perspectives are represented in the physics community, and neither has definitively won the argument. Let the argument continue in the background, unresolved. Some argue that multiverse models combined with anthropic reasoning are scientific if the underlying theories, inflation, string theory, are themselves testable in other ways. If we can confirm aspects of these theories through experiments or observations that don't involve the multiverse, then the multiverse predictions become credible, even if we can't directly observe other universes. For example, if string theory makes predictions about particle physics that we can test at accelerators, and those predictions turn out to be correct, then we'd have reason to trust the other implications of the theory, including the landscape and the multiverse. But so far this hasn't happened. String theory hasn't made confirmed predictions at accessible energies, and inflation, while successful, doesn't uniquely predict eternal inflation. Other models of inflation don't lead to multiverses. So the indirect argument for the multiverse, that it follows from well-tested theories, doesn't yet have strong empirical support. The theories aren't well-tested enough. The connections aren't tight enough. This might change. Future observations might constrain the theories more, or they might not. We'll have to wait and see. Let the waiting be patient. The string landscape lacks a mechanism for vacuum selection. This is a technical issue, but an important one. String theory tells us there are many possible vacua. It doesn't tell us which one we should expect to find ourselves in, or how the universe chooses among them. Some proposals invoke dynamics, processes that might favour certain vacua over others. But these are not universally accepted. The dynamics of vacuum selection in string theory is an open problem. an area of active research. Without a selection mechanism, the landscape becomes even harder to use predictively. We can't calculate which vacua are more likely. We can't derive the distribution of constants across the multiverse. We can only say that many possibilities exist and hope that anthropic reasoning constrains which ones we observe. This limitation is widely acknowledged. It's one reason the string landscape remains controversial, even among string theorists. The framework is incomplete. The predictions are ambiguous. The connection to observation is weak. Let that incompleteness be acknowledged without frustration. Breathe slowly. Let your thoughts settle like dust. We've been talking about abstract things, string theory, extra dimensions, vacuum landscapes, anthropic arguments. These are far from direct experience. They're mathematical structures, theoretical possibilities, ideas that might or might not describe reality. And that's okay. This is where fundamental physics lives sometimes, at the edge of what we can test, at the boundary between knowledge and speculation. The string landscape multiverse is not confirmed. It's not refuted either. It's a scenario. A way of thinking about fine-tuning and cosmology that some find compelling and others find unsatisfying. It arises from serious attempts to understand quantum gravity in the early universe. It's not frivolous, it's not pseudoscience, but it's not established fact either. It's somewhere in between, in that liminal space where science becomes speculative, where theories extend beyond data, where imagination and mathematics reach toward truths we cannot yet touch. Let yourself rest in that liminal space. Let it be a place of possibility rather than certainty. There's a question worth asking, a question that runs through all of these discussions. When does a scientific theory become too speculative? When does extending our ideas beyond what we can test stop being science and become something else? This is not a new question. It's an old one. Philosophers of science have debated it for centuries, and there's no simple answer, no clear line. Some argue that theories are scientific if they're testable in principle, even if we can't test them now. By that standard, multiverse theories might qualify if we can imagine ways, however difficult, to gather evidence for or against them. Others argue that theories must be testable in practice, not just in principle. If we can never observe other universes, never measure their properties, never confirm their existence, then appealing to them is not scientific. It's metaphysics. It's philosophy. It might be interesting, but it's not empirical science. And still others argue that theories can be scientific even if they postulate unobservable entities, as long as those entities play indispensable roles in theories that do make testable predictions. Electrons are unobservable in some sense. We don't see them directly, but we accept them because atomic theory works, because it explains countless phenomena. Maybe other universes are similar, unobservable, but part of a larger theoretical structure that makes sense of what we do observe. All of these positions are defensible, all have advocates, and the debate continues. Let the debate be part of the landscape, part of the terrain we're moving through. Falsifiability is often invoked in these discussions, the idea, due to philosopher Karl Popper, that scientific theories must be falsifiable. They must make predictions that could, in principle, be shown to be wrong. If a theory is compatible with any possible observation, if it can accommodate any outcome, then it's not scientific. Critics of the multiverse sometimes appeal to this criterion. They say that multiverse theories are unfalsifiable. No matter what we observe, we can say it's consistent with some bubble, some vacuum, some branch of the wave function. The theory is so flexible that it can't be wrong. And if it can't be wrong, it's not science. Defenders respond in various ways. Some argue that multiverse theories do make predictions, just not about other universes directly. They make predictions about the structure of the early universe, about patterns in the cosmic microwave background, about the distribution of constants in our region. These predictions can be tested. Others argue that falsifiability is too strict a criterion, that many successful scientific theories postulate entities we can't directly observe, that requiring direct testability would rule out too much. The debate is methodological. It's about what counts as good science, and it's not settled. Let the unsettled nature of this be calming rather than distressing. Some proposals suggest ways to indirectly test multiverse scenarios, to look for signatures that might hint at the existence of other universes, even if we can't see them directly. One proposal looks for bubble collisions. If our bubble, universe collided with another bubble in the distant past, it might have left an imprint on the cosmic microwave background. A specific pattern, a circular feature, something anomalous that could be detected. Searches have been conducted, data have been analysed. So far, no compelling evidence has been found. The CMB looks consistent with simple, single-universe inflationary models. No clear signs of bubble collisions have emerged. That doesn't mean they're not there. The signals might be too subtle, or we might not be looking in the right way, or our bubble might simply not have collided with any others, even if other bubbles exist. Absence of evidence is not evidence of absence, but it's also not evidence of presence. Let the ambiguity remain. Another approach looks for patterns in the data that might be explained more naturally by multiverse models than by single universe ones. Specific correlations, specific anomalies, features that would be unlikely in a simple model but natural in a multiverse. Again, searches have been conducted, and again, the results are inconclusive. Some anomalies have been reported, cold spots in the CMB, asymmetries, unexpected correlations, but none have been widely accepted as evidence for a multiverse. Most can be explained within standard models, perhaps as statistical fluctuations or systematic errors. So the observational status is this: current data do not require a multiverse. They can be explained by single universe models, but they also don't exclude a multiverse. They're compatible with multiverse scenarios too. The data, as they stand now, don't choose between the possibilities. Let that indecision be part of the stillness. No independent, direct observation of another universe has been made. That's the bottom line. No experiment has unambiguously confirmed a multiverse prediction. No measurement has detected another bubble, another vacuum, another branch. The multiverse in all its forms remains theoretical, a possibility, an implication of certain models, a scenario that might be true, but not a confirmed fact. Not yet. Perhaps not ever. That's the honest scientific assessment. That's where we are, and it's important to be clear about this, to not overstate the case, to not claim that the multiverse is real when we don't know if it's real. Science requires humility, especially at the frontiers, especially when dealing with ideas that push at the limits of what we can test. Let that humility be present in this moment. Breathe deeply. Let your body relax completely. We've covered a lot of ground. Cosmic bubbles and string landscapes, eternal inflation and vacuum states, anthropic reasoning and fine-tuning, testability and falsifiability, observations and their absence. It's a complex landscape of ideas, a tangled web of theories and arguments and critiques, and no clear path through it. No obvious answer to the question of whether the multiverse is real. That's where we are. That's the state of the science. And that's okay. Science doesn't always give us clear answers. Sometimes it gives us questions. Sometimes it gives us possibilities. Sometimes it shows us the edges of our knowledge and invites us to be comfortable there, in the uncertainty. Tonight you can rest in that uncertainty. You can let go of the need for resolution. You can allow the questions to remain questions drifting in the dark, unanswered. There's peace in that. Peace in not knowing. Peace in letting things be unresolved. Let's shift now. Let's move from the technical details, from the physics and the mathematics, to something more familiar. Something closer to everyday experience, or at least to everyday culture. Let's talk about how the multiverse appears in popular imagination, in movies and television shows, in comic books and science fiction, in the stories we tell ourselves about parallel worlds and alternate realities. Because the multiverse as a concept has captured popular imagination in ways that go far beyond physics, and it's worth understanding the difference between scientific multiverses and fictional ones, between what physicists mean when they use the word and what storytellers mean. You can rest as we explore this. Let the familiar images drift through your mind. Let them exist alongside the stranger, more abstract ideas we've been discussing. In popular fiction, the multiverse often appears as a collection of parallel worlds, alternate timelines, versions of reality where different choices were made, where different events occurred, where history unfolded differently. Maybe in one universe you took a different job, in another you moved to a different city, in another still, some historical event happened differently, changing the course of civilization. These are narrative devices, tools for exploring what-if questions, for examining how small changes can cascade into large differences, for creating drama and conflict and interesting character interactions. And they're compelling. We're drawn to these stories. We like imagining how things might have been different. We like seeing familiar characters in unfamiliar circumstances. We like the idea that somewhere, somehow, another version of us is living a different life. But these fictional multiverses, as engaging as they are, don't correspond closely to the scientific ones we've been discussing. Let that distinction begin to form. In movies and shows, characters often travel between universes. They step through portals, use devices, perform rituals, and suddenly they're in another world. A world that looks similar to theirs but differs in key ways, and they can interact with that world. They can meet alternate versions of themselves. They can change things. They can return home, usually. This is a powerful narrative tool. It allows for all sorts of storytelling possibilities. Alternate versions of characters. Moral dilemmas about which world is real or which deserves to be saved. Comedic situations where different versions meet. Dramatic confrontations between choices made and not made. but it doesn't match the physics. In the scientific multiverse scenarios we've discussed, travel between universes is not just difficult, it's impossible, or effectively impossible, according to the theories that propose these multiverses. Let's think about why. In the Level 1 and Level 2 multiverses, the ones arising from eternal inflation, other regions are separated from us by enormous distances, and in many models they're separated by regions of space that are still inflating, still expanding faster than light. The distance between bubbles grows faster than any signal can cross it. So you can't travel there, you can't send a message, you can't even, in principle, observe what's happening in another bubble. The causal structure of space-time prevents it. The physics itself makes it impossible. These other universes, if they exist, are forever beyond our reach. Not because we lack the technology, but because the geometry of space-time doesn't permit contact. It's not a practical limitation. It's a fundamental one. That's very different from the fictional multiverse, where portals can be opened, where travel is difficult but achievable, where the barriers between worlds can be crossed with the right knowledge or device. Let the difference settle. In the quantum multiverse, the Level 3, many-world scenario, the situation is even more abstract. The other universes aren't places. They're not located somewhere else in space. They're different branches of the wave function, different components of the quantum state, and branches, once they've decohered, don't interact. That's what decoherence means. The different components become effectively independent. They evolve separately. They don't interfere with each other. They can't be recombined. So you can't jump from one branch to another. You can't visit the version of yourself that observed a different outcome. That version exists according to the interpretation, but it exists in a different term of the wave function, in a different part of the quantum configuration space. There's no mechanism for travel, no portal, no device. The branches are separated not by distance but by decoherence, by the irreversible spreading of quantum correlations into the environment. It's not a spatial separation, it's a much stranger kind of separation, one that doesn't admit of traversal. Let that strangeness rest, without trying to visualize it too concretely. Popular fiction often treats alternate histories as variations on personal choices. In one universe, you chose to marry this person. In another, you chose someone else. In one, you took this job. In another, you pursued a different career. And the implication is that each choice spawns a new universe. That your decisions, your actions, your moments of free will create branching realities. This is compelling dramatically. It raises questions about responsibility, about regret, about the paths not taken. It suggests that all possibilities are realized somewhere, that every version of your life is lived by some version of you. But it's not how the scientific multiverse works, even the quantum one. In the many worlds interpretation, branching happens because of quantum events, because of decoherence at the microscopic level, not because of conscious choices. Your decision to take a job doesn't split the universe, but the countless quantum events occurring in your brain, in the environment, in the particles around you, those create branching constantly, at every moment, and most of those branches are incredibly similar. They differ by tiny, insignificant details. A photon here instead of there, a particle decaying now instead of a nanosecond later. The branches where your life is dramatically different, where you made a different choice, are no more special than any other branches. They're just particular configurations among infinitely many. And they're not caused by your choice. They exist in parallel as different quantum amplitudes, whether you feel like you chose or not. Let the gap between narrative and physics be clear. In scientific discussions, when physicists talk about copies of you in distant regions of a level 1 multiverse, they're making a statistical argument. If space is infinite and matter is distributed similarly everywhere on average, then given enough distance you'll eventually find a region with the same arrangement of particles as here. Same atoms in the same configuration. Same history, effectively. But this isn't about your choices creating copies, it's about probability, about the fact that in an infinite space even extremely unlikely configurations will occur somewhere, including configurations identical to this one. It's a strange conclusion, unsettling perhaps. But it's not about alternate versions living different lives based on different decisions. It's about the mathematics of infinity, about what happens when you have endless space and finite configurations. The copies, if they exist, aren't aware of each other, can't communicate, aren't connected in any meaningful way except statistical. Let that version of copies be distinct from the narrative version. Popular fiction loves the idea of meeting yourself, of confronting an alternate version, of seeing what you might have been. It's a powerful image. It raises questions about identity, about continuity, about what makes you you. But in the scientific multiverse scenarios, this doesn't happen. Can't happen for the reasons we've discussed. The other versions are causally disconnected, separated by insurmountable distances or by the structure of quantum mechanics itself. You will never meet your alternate self. You will never know what different choices led to. You will never have the chance to compare lives to see which version is happier, more successful, more fulfilled. If other versions exist, they exist in isolation, each convinced that their world is the only world, each unable to detect the others. That's the scientific picture. It's less dramatic, less satisfying narratively, but it's what the physics suggests. Let the loss of that narrative possibility be okay. Science fiction sometimes tries to engage with real physics. Some stories incorporate ideas from quantum mechanics, from cosmology, from relativity. They try to ground their multiverses in something that sounds scientific, that uses the right vocabulary, and that's fine. It's interesting. It can be done well, but it's important to recognize that even the most scientifically informed fiction is still fiction. It takes liberties, it simplifies, it prioritizes story over accuracy. The physicist Brian Greene wrote a book about the multiverse for a general audience, explaining the real scientific ideas. The book was careful, precise, grounded in actual theory. But even that book, written by a physicist for a popular audience, is different from a technical paper. It's different from the cutting-edge research. It's an interpretation, a translation, a way of making abstract ideas accessible. And movies, TV shows, comic books, they're even further from the source. They use the language of multiverses. They invoke quantum mechanics or parallel dimensions. But they're telling stories, creating entertainment. The physics is backdrop, not substance. Let that be understood without judgment. fiction serves different purposes than science. Both are valuable, but they're not the same. There's something worth appreciating about fictional multiverses, though, about the way they've brought these ideas into popular consciousness, about how they've made people aware of the concept, even if the details are wrong. More people know the word multiverse now than did 20 years ago. More people have thought about alternate realities, parallel worlds, branching possibilities, and some of those people might be inspired to learn the real physics, to dig deeper, to find out what scientists actually think. Fiction can be a gateway, a starting point, an invitation to curiosity. So even though fictional multiverses don't match scientific ones, they serve a purpose. They spark imagination. They raise questions. They make the abstract concrete, even if the concreteness is illusory. Let that contribution be acknowledged. Breathe slowly. Let your mind wander through the images you've seen, the movies you've watched, the stories you've read. Let them coexist with the physics. Let the Marvel multiverse and the many worlds interpretation share space in your thoughts without one needing to replace the other. They're different things, different kinds of ideas, different ways of thinking about possibility and reality. One is entertainment, one is science. Both are human creations. Both reflect our desire to understand, to imagine, to explore beyond what's immediately visible. And that desire is worth honouring, worth celebrating, even when it leads us to places where science can't follow, even when it takes us into pure imagination. Let the distinction be clear, but let both exist. When physicists use the word multiverse, they're usually not thinking about narrative possibilities. They're not thinking about character drama or alternate timelines or versions of themselves living different lives. They're thinking about mathematics, about equations and their implications, about what theories predict when you follow them consistently, about the structure of space-time or quantum mechanics or fundamental fields. It's abstract, technical, removed from everyday experience, and that's appropriate. That's what physics is. It's not storytelling. It's not personal. It's an attempt to understand the impersonal laws that govern reality, to find patterns, to make predictions, to test those predictions against observation. The multiverse in physics is a technical consequence of certain theories, not a place to visit, not a narrative device, not a reflection of personal choices. It's a feature of the mathematics, a possibility in the equations, a scenario that might or might not describe the actual structure of reality. Let that technical, impersonal nature be present. Some physicists dislike the popularization of multiverse ideas precisely because it creates confusion. Because people hear multiverse and think of movies, think of alternate versions of themselves, think of dramatic confrontations and portal-jumping adventures, and then when physicists try to explain what they actually mean, there's a mismatch, a disconnect. The popular conception gets in the way of understanding the real idea. This is a perennial problem in science communication. How do you talk about abstract ideas to a general audience without the metaphors and simplifications becoming more vivid than the reality? How do you use familiar concepts to explain unfamiliar ones without the familiarity overwhelming the unfamiliarity? There's no perfect answer. Communication always involves trade-offs. Precision versus accessibility. Accuracy versus engagement. The best we can do is be clear about the limitations, to say, this is a metaphor, this is a simplification. The real thing is stranger and more abstract. Let that acknowledgement be part of how we hold these ideas. The multiverse in popular culture serves a different function than the multiverse in physics. In culture, it's about exploring human concerns, identity, choice, consequence, regret, possibility. It's a mirror for our anxieties and desires. In physics, it's about explaining observations, about making sense of fine-tuning, about following theories to their logical conclusions, about the structure of reality at the deepest levels. Both are valid, both are interesting, but they're not the same thing. And it's worth keeping that distinction in mind. Worth remembering that when a physicist says multiverse, they mean something very different from when a screenwriter says it. The words are the same, the concepts are not. Let that divergence be clear. There's a certain irony here. The scientific multiverse, the one arising from real physics, is in some ways more alien, more incomprehensible than the fictional one. The fictional multiverse is human-scaled. You can walk through it, meet people, have conversations, make choices. The scientific multiverse is inhuman, vast beyond comprehension, structured by mathematics we can barely grasp, inaccessible, unvisitable, perhaps undetectable. It's not designed for narrative. It's not shaped by human concerns. It emerges from impersonal laws, from the structure of space-time and quantum mechanics and fundamental fields. And in that sense, it's more truly alien than anything fiction has invented. More strange, more removed from everyday experience, but also perhaps more real, or at least possibly real, grounded in theories that have been tested, that work, that describe other aspects of reality successfully. Let both the strangeness and the possible reality coexist. Breathe again. Let the tension between fiction and science dissolve. We've walked through this distinction now, between Marvel worlds and quantum branches, between portal-jumping adventures and eternal inflation, between personal choices creating universes and decoherence-splitting wave functions. The gap is large, the difference is fundamental, but both kinds of multiverses, the fictional and the scientific, are products of human imagination. Both reflect our desire to think beyond the visible, to imagine more than what's immediately present. And that desire, that impulse to imagine, is worth honouring, even when the imagined doesn't match the real, even when the story diverges from the science. We are creatures who imagine, who tell stories, who build theories, who ask what if in both narrative and mathematical forms. Let that commonality be recognised even as the differences remain clear. Now, let's turn to something deeper. Something that underlies all of these discussions. Let's talk about what counts as science. What makes an idea scientific versus speculative? Where the boundaries lie, where they blur. This is philosophy of science. It's methodology. It's about the nature of knowledge and evidence and explanation, and it's central to the multiverse debate. You can rest as we explore this. These questions don't demand answers. They can simply exist, floating in the quiet, as questions that have been asked for centuries and will continue to be asked. Science, as we usually understand it, is empirical. It's based on observation, on measurement, on testing predictions against what we actually see in the world. A scientific theory makes predictions. You design experiments or observations to check whether those predictions are correct. If they are, the theory gains support. If they're not, the theory is wrong, or at least incomplete, and needs to be revised or replaced. This is the basic picture, the ideal. Science as a process of hypothesis, prediction, test, revision, and it works. It's given us an extraordinary understanding of the natural world, from atoms to galaxies, from bacteria to ecosystems, from chemical reactions to quantum fields. The empirical method, applied carefully and repeatedly, has built our modern scientific knowledge. But what happens when a theory makes predictions about things we can't observe? About entities that are, in principle or in practice, beyond our reach? That's where the multiverse sits, and that's where the philosophical questions arise. Let them arise slowly, without urgency. Some entities we accept in science are not directly observable. Electrons, for instance. We don't see electrons. We can't watch them moving through a wire. They're too small, too fast, too quantum mechanical. But we accept that electrons exist because atomic theory, the theory that includes electrons, explains so much. It explains chemistry. It explains electricity. It explains the periodic table, the behavior of materials, the properties of light. The theory makes countless testable predictions, and those predictions are confirmed. So we infer that electrons are real, even though we don't observe them directly. This is a common move in science, postulating unobservable entities because they play indispensable roles in theories that work. The entities are inferred, not observed, but the inference is justified by the success of the theory. Some philosophers of science call this scientific realism, the view that successful theories are at least approximately true, and that the entities they postulate really exist. Let that position rest in your mind. Now, could the same logic apply to other universes? Could we infer their existence, even if we can't observe them, because they're part of theories that work? Some argue yes. If eternal inflation is confirmed, if we find strong evidence that inflation happened in a way that naturally leads to eternal, self-reproducing expansion, then other bubble universes would be a consequence of that theory. Not something we add by hand, but something that follows from the physics. Similarly, if the many worlds interpretation of quantum mechanics turns out to be the best way to make sense of quantum theory, if it resolves problems that other interpretations struggle with, then we might accept the reality of other branches, even though we can't observe them. The entities would be inferred, like electrons, accepted because of their role in successful theories. That's the argument for scientific realism about the multiverse. Let it exist as one possibility. But there's a counter-argument, a strong one. Electrons, quarks, and other unobservable entities in standard physics are not completely disconnected from observation. They have observable consequences. They affect things we can measure. We don't see electrons, but we see their effects. The current flowing, the light emitted, the patterns in particle collisions. The theory makes predictions about those effects, and we can test them. Other universes, by contrast, might be completely causally disconnected. In eternal inflation models, other bubbles are beyond our horizon. They don't affect anything in our region. They leave no observable trace. In many worlds' quantum mechanics, other branches are separate. They don't interfere. They can't be detected once decoherence has occurred. So the analogy to electrons breaks down. Electrons affect observations. Other universes might not. And if they don't, if they're truly causally disconnected, then the inference to their existence becomes much more tenuous. This is the empiricist critique. The view that scientific theories should only postulate entities that make a difference to observations, that if something has no observable consequences, accepting it is metaphysics, not science. Let that critique exist alongside the realist position. There's a related concept called underdetermination, the idea that multiple theories can fit the same data, that observations don't uniquely determine which theory is correct. For instance, you could have two theories that make identical predictions for everything we can observe, but that differ in their claims about unobservable things. One postulates a multiverse, the other doesn't, but both explain all the same observations. In that case, how do we choose between them? What grounds the choice? Some say we use other criteria: simplicity, elegance, explanatory power, fit with other theories we accept. These are called theoretical virtues. They're not empirical in the strict sense, but they guide theory choice when data alone don't decide. Others say that if two theories make the same observable predictions, then the choice between them isn't scientific, it's philosophical or aesthetic. Both theories are empirically equivalent, so science can't adjudicate. This is a deep methodological question, and it applies directly to the multiverse. If multiverse models and single universe models both fit the data, both explain what we see, then choosing between them might not be a purely scientific matter. Let the ambiguity of that be present. Falsifiability is another concept that arises here. Philosopher Karl Popper argued that scientific theories must be falsifiable. They must make predictions that could, in principle, be shown wrong. A theory that's compatible with any possible observation is not scientific because it can't be tested. Critics of the multiverse often appeal to falsifiability. They argue that multiverse theories are unfalsifiable because no matter what we observe, we can always say it's consistent with some part of the multiverse. If the cosmological constant is large, we're in a bubble where it's large. If it's small, we're in a bubble where it's small. The theory accommodates anything, so it predicts nothing. This is a serious criticism. It suggests that multiverse theories, despite emerging from respectable physics, have crossed a line, that they've become untestable in a way that removes them from the domain of science. Defenders of multiverse theories respond in various ways. Some argue that the theories do make predictions, just not about other universes directly. They make predictions about patterns in our universe, about the CMB, about the distribution of galaxies, about the likelihood of different values for constants. Others argue that falsifiability is too strict, that it would rule out too many things we legitimately consider scientific. That inference to unobservable entities is common in science and doesn't require direct falsification. The debate continues. Neither side has won decisively. Let the debate remain unresolved, hovering in the stillness. Some defend the multiverse as genuinely scientific, even while acknowledging that it's at the frontier. They say that science has always pushed beyond the immediately observable, that theories have always made claims about things we can't directly see, that the multiverse is just the next step in that process. They point out that many things we now accept were once considered too speculative. Atoms, molecules, distant galaxies, black holes, all were theoretical postulates before they were confirmed. All faced skepticism. all were eventually accepted because the theories that included them were successful. Maybe the multiverse is similar. Maybe future observations will constrain multiverse models. Maybe we'll find indirect evidence that makes some versions more plausible than others. Maybe what seems untestable now will become testable with better instruments, better theories, better understanding. Or maybe not. Maybe the multiverse will remain forever beyond empirical reach. Maybe it's genuinely different from atoms and black holes. Maybe it represents a limit to what science can address. We don't know yet. The question is open. Let the openness be comfortable. Anthropic reasoning, which we discussed earlier, is another methodological issue. Is it legitimate to explain observations by appealing to the fact that observers can only exist in certain conditions? Some say yes. Anthropic reasoning is just a selection effect. It constrains where we can find ourselves. It's not circular or unscientific. It's a recognition that our existence provides information about the kind of universe we inhabit. Others say no. Anthropic reasoning is too weak. It explains why we observe life-compatible conditions, but it doesn't explain why those conditions exist. It doesn't predict the specific values of constants. It just says they must be in a certain range, which is not very constraining. And there's a worry about explanatory regress. If we explain the constants by appealing to a multiverse, we've just shifted the question. Now we need to explain why the multiverse exists, why it has the structure it does, why the landscape of possibilities takes the form it does. Have we really explained anything? Or have we just moved the mystery one level up? These are philosophical questions. Questions about what counts as explanation, what satisfies our desire to understand. Let them be questions without demanding answers. Probability in an infinite multiverse is particularly problematic. This is the measure problem we mentioned earlier, but it's worth revisiting because it's both technical and philosophical. If there are infinitely many regions, infinitely many bubbles, infinitely many branches, how do you calculate what a typical observer should see? You can't just count outcomes, because every outcome occurs infinitely many times. Different ways of assigning probabilities, different measures, give different answers, and there's no obvious way to choose among them. No principle that uniquely determines the correct measure. This is more than a technical difficulty, it's a conceptual problem. If the theory doesn't tell you what to expect, if it doesn't make definite predictions even in principle, then in what sense is it scientific? Some researchers are working on this problem, trying to find principles that constrain the measure, that make predictions more definite. But so far, there's no consensus solution. The problem remains open, and while it remains open, the multiverse theories that depend on it remain incomplete. Let that incompleteness be acknowledged. Breathe for a moment. Let the philosophical complexity settle. These are not easy questions. They don't have clear answers. They involve fundamental issues about the nature of science, of knowledge, of explanation. And it's okay. These are questions that scientists and philosophers have been grappling with for decades. They're not going to be resolved tonight. They're not going to be resolved in a single conversation, a single paper, a single lifetime perhaps. They're part of the ongoing work of understanding what science is and what it can tell us. They're part of the human effort to make sense of the world and our place in it. And they're particularly acute when it comes to the multiverse. because the multiverse pushes at the boundaries. It tests the limits of what we mean by science. It forces us to ask hard questions about observation and inference and explanation. Let those questions exist without pressure. Let them be part of the landscape of thought. There's a view that says multiverse theories are scientific as long as they arise from theories that are testable in other ways. As long as inflation, string theory, quantum mechanics, the frameworks that predict multiverses, make other predictions that we can check. This is a pragmatic approach. It doesn't require that every consequence of a theory be testable. It just requires that the theory as a whole be testable, that it be grounded in empirical success. By this standard, multiverse theories might qualify. Quantum mechanics is extraordinarily well tested. Inflation is supported by CMB observations. String theory, while less confirmed, is at least constrained by consistency requirements and connections to other physics. So even if we can't test the multiverse parts directly, we can test the underlying theories, and if those theories are successful, then their implications, including multiverses, gain credibility. This is a reasonable position, but it's not universally accepted. Critics argue that it's too permissive, that it allows theories to make untestable claims as long as they make some testable ones, that it weakens the empirical constraint too much. Again, the debate is not resolved. Let both positions coexist. Some scientists are comfortable saying that the multiverse question might not be decidable by science, that it might be a question where empirical methods reach their limit, where physics transitions into metaphysics, and they're okay with that. They see it as a recognition of science's boundaries, an acknowledgement that not every question can be answered empirically, that some questions about reality might remain forever beyond our reach. This doesn't mean giving up. It means being realistic, being honest about what we can and can't know, being careful not to claim more certainty than we have. It's a humble position, a recognition that science, powerful as it is not unlimited, that there are things we might never be able to test, and that's okay. That's just how reality is. Others find this unsatisfying. They want science to be able to address any question about the physical world. They resist the idea of permanent limits. They hope that what seems untestable now will become testable later, with better technology, better theories, better insights. And maybe they're right. Maybe there are no permanent limits. Maybe every question can eventually be addressed. Or maybe the multiverse represents a genuine boundary, a place where science ends and something else begins. We don't know. Let the not knowing be restful. Philosophy and science have always been intertwined. Scientists make philosophical assumptions, even if they don't always acknowledge them, about what's real, about what counts as evidence, about what makes a good explanation. And philosophers engage with science, trying to understand what scientific theories are telling us about the world, trying to make sense of the methodology, trying to resolve conceptual puzzles. The multiverse brings these interactions to the foreground. It makes the philosophical questions explicit. It forces both scientists and philosophers to think carefully about what they're doing, what they're claiming, what justifies their claims, and that's valuable. Even if it doesn't lead to clear answers, even if it leaves us with ongoing debates and unresolved tensions, the questions themselves are worth asking. The process of thinking through them is worth engaging, even when, especially when the conclusion is uncertainty. Let the value of the questions be recognized. Breathe deeply, let your thoughts slow. We've been exploring the boundaries of science, the edges of what we can know, the places where empirical methods reach their limits or seem to. It's abstract, it's philosophical, it's far from concrete experiment and observation. But it's important, because if we're going to talk about the multiverse, if we're going to take these ideas seriously, we need to understand what kind of ideas they are, what their status is, what grounds them, what limits them. And the answer is complex. The multiverse is not confirmed science, it's not established fact, but it's not pseudoscience either. It's not arbitrary speculation, it's somewhere in between, emerging from successful theories motivated by real physics, but extending beyond what we can currently test. Perhaps beyond what we can ever test. It's at the frontier, and frontiers are always uncertain, always contested, always alive with debate and possibility. Let that frontier be a place of rest rather than anxiety tonight. Let's gather together now some of the challenges, some of the difficulties, some of the reasons why multiverse ideas, despite their emergence from serious physics, remain controversial and uncertain. We've touched on some of these already, but it's worth bringing them together, worth seeing the full picture of what multiverse models struggle with, what problems remain unsolved, what makes physicists skeptical, even those who work on these ideas. You can let these difficulties wash over you. They don't need to be resolved. They can simply exist as part of the landscape, as features of the territory we're exploring. The measure problem keeps appearing. It's central to eternal inflation scenarios. If inflation produces infinitely many regions, infinitely many bubbles, then how do you calculate probabilities? How do you predict what a typical observer should see? This is not just a technical detail, it's fundamental. Without a way to assign probabilities, the theory can't make definite predictions. It can't tell you what to expect. It becomes much harder to test, much harder to use scientifically. Different measures, different ways of counting or weighting regions, give different answers. Some measures predict the typical observers should see one set of conditions. Other measures predict different conditions. And there's no agreed upon principle for choosing the right measure. Researchers have proposed various approaches, some based on proper time, some on volume, some on observer counts, but none has achieved consensus. The problem remains open after decades of work. This is a serious limitation, one that advocates of eternal inflationic knowledge, one that makes the framework incomplete. Let that incompleteness be present without judgment. Eternal inflation requires assumptions about physics at very high energies, energies far beyond what we can produce in particle accelerators, energies close to the Planck scale, where quantum gravity becomes important. And we don't have a confirmed theory of quantum gravity. We have candidates: string theory, loop quantum gravity, others, but no experimental verification. No direct evidence that any of these frameworks correctly describes nature at those energies, so eternal inflation is built on uncertain foundations. It depends on extrapolating our theories far beyond where they've been tested. And those extrapolations might be wrong. The physics at very high energies might be different from what we expect. The scalar field behavior that drives inflation might not work the way the models assume. This doesn't mean eternal inflation is wrong. It means it's speculative. It means we're extending our theories into regimes where we're not sure they apply, and their extension might not be reliable. It's an honest uncertainty, one that needs to be acknowledged. Let it be acknowledged now, in the quiet. The string landscape suffers from similar issues. String theory itself is not empirically confirmed. It makes predictions at energy scales we can't access. It's mathematically elegant, internally consistent, but not yet tested against observation. And even within string theory, the landscape is uncertain. The claim that there are 10 to the 500 vacua depends on specific calculations, specific assumptions about compactification and stabilization of extra dimensions. Those calculations might be wrong. The assumptions might not hold. Moreover, there's no mechanism for vacuum selection that's universally accepted. No agreed upon way to determine which vacuum we should find ourselves in, or how to calculate the distribution of vacua that eternal inflation might populate. So the landscape is a theoretical construct within a theoretical framework. It's speculation within speculation. 2 layers of uncertainty compounding. This doesn't invalidate it, but it means we should hold it lightly, should recognize its speculative nature, should not treat it as established fact. Let that lightness be present in how we think about it. In quantum mechanics, the many worlds interpretation faces its own challenges. The emergence of probability is one. If all outcomes occur in different branches, why do we experience some outcomes more often than others? How do we derive the Born rule, the rule that tells us probabilities, from the Everettian framework? This is an active research area. Some approaches try to derive the Born rule from decision-theoretic considerations, from rational betting behavior, from symmetries in the wave function structure, and some researchers claim to have solved the problem, but others remain unconvinced. They argue that the derivations make hidden assumptions, that they smuggle in probability where they claim to derive it, that the problem is deeper than proposed solutions acknowledge. The debate is technical, it's ongoing, and it's not resolved. Let the unresolved nature of this be part of the picture. Another issue with many worlds is the ontological cost, the claim that infinitely many branches exist, all equally real, all containing conscious observers, all experiencing different outcomes. This is an enormous multiplication of entities, a vast proliferation of unobservable worlds. And some philosophers and physicists argue that parsimony, preferring simpler theories with fewer entities, should count against it. Defenders respond that the branches aren't added, they're already in the wave function, the mathematics already contains the structure. Everett just interprets it literally rather than adding collapse, but critics say this is disingenuous, that choosing to interpret the mathematical structure as real branches is still a choice, that other interpretations don't make that choice and therefore postulate fewer entities. It's a philosophical disagreement about what counts as simple, about what we should prefer when theories are empirically equivalent. And like many philosophical disagreements, it's not resolved by data. Let it remain a matter of perspective. Some physicists have written papers specifically criticizing many worlds, arguing that it doesn't solve the problems it claims to solve, that it introduces new difficulties while attempting to remove old ones, that it's not as elegant or simple as its proponents claim. These critiques point to issues like the preferred basis problem. Why do we experience a particular branching structure rather than some other decomposition of the wave function? They point to the difficulty of defining worlds or branches precisely. They point to the challenge of explaining subjective experience in a framework where all outcomes occur, and they argue that the metaphysical cost is too high, that postulating infinitely many unobservable worlds is a radical move that should require extraordinary justification, and that the justification offered is not extraordinary enough. These are serious critiques published in peer-reviewed journals written by thoughtful physicists. They don't prove many worlds is wrong, but they show that it's not obviously right either, that the interpretation remains contested. Let the contestation be visible. Across all multiverse scenarios, inflationary, string landscape, quantum, there's a common thread. They depend on extrapolating successful theories into domains where those theories haven't been tested, where we're not sure they still apply. Inflation works well to explain the observable universe, but does it work at the extreme energies where eternal inflation operates? We don't know. Quantum mechanics is extraordinarily successful, but does the Schrödinger equation continue to hold at all scales, in all circumstances, without modification? We don't know. String theory is mathematically rich, but does it correctly describe nature? Does the landscape actually exist? We don't know. The extrapolations might be justified. The theories might remain valid in those regimes, but they might not. And we don't currently have empirical access to check. This is the fundamental uncertainty. The theories we're extending are successful where we've tested them, but we're extending them far beyond those tests, and that extension is not guaranteed to be reliable. Let that uncertainty be central. Breathe for a moment. Feel the weight of these challenges, the accumulation of difficulties, the layers of uncertainty. It's a lot. It's heavy. It suggests that multiverse ideas, despite emerging from respectable physics, rest on uncertain foundations, that they're speculative in ways that should make us cautious. And that's true. We should be cautious. We should recognize the speculative nature of these ideas, should not overstate their support, should not claim they're established when they're not. But being cautious doesn't mean dismissing them, doesn't mean ignoring them. These are serious ideas taken seriously by serious researchers. They arise naturally from our best current theories. They address real puzzles. The challenges are real. The uncertainties are real. But so is the motivation. So is the connection to tested physics. Both things can be true. The ideas can be speculative and still worth pursuing, can be uncertain and still interesting. Let both be present. Many physicists who work on multiverse-related topics are themselves cautious. They're aware of the limitations. They acknowledge the speculative nature of their work. They don't claim to have proven that other universes exist. What they claim is more modest, that multiverse scenarios are possibilities worth exploring, that they emerge naturally from certain frameworks, that they might help us understand features of our universe that are otherwise puzzling. They're investigating, calculating, exploring the implications, trying to find ways to make predictions, to connect to observations, to test the ideas more rigorously. and they're honest about where things stand, about what's known and what's not, about what's confirmed and what's speculative. This is how science works at the frontier. You pursue ideas that seem promising, even when they're uncertain. You try to make them more precise, more testable, more connected to observation. You remain open to the possibility that you're wrong. It's an honest, humble approach, one that acknowledges the difficulty of the questions while still engaging with them seriously. Let that approach be appreciated. Some prominent physicists have argued against multiverse ideas, have written papers and books explaining why they think these ideas go too far, why they think the evidence is insufficient, why they worry about the methodology. These critics are not anti-science. They're not dismissive of theoretical work. They're often accomplished cosmologists, quantum physicists, string theorists themselves. They understand the technical details. They've engaged deeply with the arguments, and they've concluded that multiverse ideas, as currently formulated, don't meet the standards they think science should maintain, that they're too speculative, too weakly connected to observation, too dependent on unverified assumptions. Their criticisms should be taken seriously. They represent thoughtful engagement with the issues. They raise important methodological concerns, and they remind us that the physics community is not unanimous, that there's genuine disagreement, that consensus has not been reached. Let that lack of consensus be part of the landscape. The criticisms often focus on falsifiability, on the worry that multiverse theories can accommodate any observation, that they're too flexible, that they predict everything and therefore predict nothing. This is particularly acute for anthropic arguments combined with the landscape. If there are 10 to the 500 vacua, with every possible value for every constant represented somewhere, then any value we observe can be explained anthropically. We observe this value because we're in a vacuum with this value, and we couldn't observe anything else because observers can only exist in certain ranges. But this doesn't predict the specific value. It just says it must be in some life-compatible range. That's a very weak constraint. It's consistent with a huge variety of observed values. Critics argue this is not real explanation, not real prediction. It's post hoc accommodation, fitting the theory to the data after the fact rather than predicting the data beforehand. And without prediction, without the ability to be surprised by observations, the theory loses much of its scientific force. This is a weighty criticism, one that defenders struggle to fully address. Let the difficulty of addressing it be visible. The dependence on anthropic reasoning is itself problematic. Even if you accept that anthropic selection is a legitimate scientific principle, and not everyone does, applying it requires knowing what conditions are necessary for observers, and we don't know that with precision. We know roughly what kind of universe can support complex chemistry, stable atoms, long-lived stars. But the details are uncertain. How much can you change the constants and still get observers? We don't have exact answers. Different assumptions about what's necessary for observers lead to different anthropic predictions. The framework doesn't give unique answers, and there's a deeper worry. If you're willing to appeal to observers to explain constants, why stop there? Could any feature of physics be explained anthropically if you're creative enough? Does this kind of reasoning have limits? These are methodological concerns about whether anthropic reasoning, even if sometimes legitimate, is being applied too broadly, whether it's being used to avoid the hard work of finding deeper explanations. Let those concerns exist without resolution. Across all these challenges, the measure problem, the unverified high-energy physics, the ontological costs, the weak predictivity, the heavy reliance on anthropic arguments, there's a pattern. Multiverse ideas push at the boundaries of what we can test, what we can confirm, what we can know empirically, and that raises questions about whether they're still science, whether they've crossed into metaphysics or philosophy, whether they're the kind of thing that physics can legitimately address. Different people draw the line in different places. Different people have different intuitions about where science ends and speculation begins. There's no objective answer, no clear demarcation, just ongoing debate, ongoing negotiation, ongoing efforts to clarify what we mean by science and what standards we should apply. The multiverse sits right at that boundary, right in the contested territory, and that's why it's so interesting and so controversial. Let it sit there in that contested space without needing to be resolved. Breathe deeply, let the challenges dissolve into the background. We've walked through the difficulties. Now, the reasons for skepticism, the problems that remain unsolved, the ways in which multiverse ideas, despite their grounding in real physics, remain speculative and uncertain. It's important to see this, to not be overly credulous, to recognize that these are frontier ideas, not established facts, that serious scientists disagree about them, that the evidence is not compelling, at least not yet. But it's also important not to dismiss them entirely, not to think they're nonsense or pseudoscience. They're serious theoretical possibilities, emerging from serious physics, addressed by serious researchers. They're uncertain, but they're not frivolous. Let both things be true. Let the uncertainty coexist with the seriousness. Let's turn now toward what we don't know, toward the open questions, the unresolved issues, the places where research continues, where understanding might deepen, where future observations might constrain or clarify or surprise us, because science is not static, it's ongoing. What's uncertain now might become clearer later. What seems untestable now might become testable with new instruments, new insights, new theoretical developments, or it might not. Some questions might remain permanently beyond our reach, but the future is open, the questions are alive. And there's something peaceful in acknowledging that, in recognizing that we're in the middle of a story, not at its end. You can rest as we explore this open future. Let the possibilities drift through your mind without attachment, without needing to know which will be realized. We still don't know whether inflation happened in an eternally self-reproducing form. We have evidence that inflation occurred. The cosmic microwave background supports it. The large-scale structure of the universe supports it. But the evidence constrains only the inflation that affected our observable region. Whether inflation continued elsewhere, whether it's still happening in distant regions, whether it created a multiverse of bubbles, these questions remain unanswered. Future observations might help. More precise measurements of the CMB might reveal patterns that favour some inflation models over others. Detection of primordial gravitational waves, ripples in space-time left over from the inflationary epoch, might tell us about the energy scale of inflation and constrain the field dynamics. These observations are planned. Experiments are being designed, satellites are being built, data will come in over the next decades that will help us understand inflation better, and that might indirectly tell us whether eternal inflation is plausible, whether the models that predict it are on the right track, or the data might point in a different direction, might suggest that inflation was a one-time event, that a different mechanism operated, that the multiverse is not necessary to explain what we see. We don't know yet. The future will tell us more. Let the openness of that future be calming. We don't have a complete, empirically verified theory of quantum gravity, and we won't, probably, for a long time. The energies where quantum gravity becomes important are far beyond what our accelerators can reach, far beyond what we can probe directly. But indirect constraints are possible. Observations of black holes, of gravitational waves, of the early universe might tell us something about how gravity behaves in extreme conditions, might favour some approaches over others. String theory, loop quantum gravity, and other candidates make different predictions, or at least have different structures. As our understanding deepens, as our observations become more precise, we might be able to narrow the possibilities, to rule out some frameworks, to gain confidence in others, and that would affect multiverse discussions, because many multiverse scenarios depend on assumptions about quantum gravity, about extra dimensions, about the behavior of fields at very high energies. If we learn more about quantum gravity, we'll learn more about whether those assumptions are justified, whether the multiverse scenarios built on them are plausible. This is long-term work, decades, perhaps centuries, but it's ongoing, and it might eventually give us clearer answers. Let that long timescale be acceptable. Let the work continue slowly, patiently, without rush. In quantum mechanics, the interpretation question remains open. Many worlds, Copenhagen, objective collapse, pilot wave theories, consistent histories, all are still discussed. All have advocates. None has achieved universal acceptance. Research continues on decoherence, on the emergence of classicality from quantum theory, on the measurement problem and how different approaches address it, on the mathematical structure of quantum mechanics and what it might tell us about ontology. And sometimes progress is made, new theorems are proven, new perspectives emerge, old arguments are clarified or refined, the landscape of interpretational options becomes better mapped. It's possible that someday we'll have a clearer sense of which interpretation is correct, or we might develop new experiments that distinguish between them in ways we haven't thought of yet. Experiments involving quantum gravity, perhaps, or macroscopic quantum systems, or novel states of matter, or it might remain interpretational forever, a question that physics can't answer, because all interpretations fit the data equally well. We don't know. But the investigation continues, and that continuing investigation is itself valuable. Even if it doesn't lead to definitive answers, it deepens our understanding of what quantum mechanics says and what it might mean. Let the value of the investigation be recognized, independent of whether it resolves the question. Next-generation cosmological surveys will map the universe in unprecedented detail. They'll measure the distribution of galaxies with enormous precision. They'll observe the cosmic microwave background at higher resolution. They'll detect more gravitational wave events from the early universe, perhaps. All of this data will constrain our models, will tell us more about the history of the cosmos, about the early universe, about the nature of dark energy and dark matter, about the geometry of space-time. And indirectly, this might bear on multiverse questions. If certain inflationary models are ruled out, that affects eternal inflation scenarios. If the cosmological constant is measured more precisely, that affects anthropic arguments. If unexpected patterns appear in the data, that might hint at physics beyond our current understanding. The observations won't directly detect other universes, but they'll constrain the theories that predict them. They'll narrow the space of possibilities. They'll give us a better sense of which scenarios are plausible and which are not. This is how science often works: indirect constraints, gradual narrowing of possibilities, slow accumulation of evidence that favours some frameworks over others. It's patient work, but it's real progress. Let that gradual progress be enough. There are proposals for new kinds of observations, searches for specific signatures in the CMB that might indicate bubble collisions, searches for patterns in the distribution of matter that might reflect features of the inflationary landscape, searches for anomalies that don't fit simple models, but might fit multiverse ones. These searches are speculative. They're fishing expeditions in some sense, looking for signals we're not sure exist. But that's how discovery sometimes happens. You look for the unexpected. You search in places where theoretical consideration suggests something might be hiding. So far, nothing compelling has been found, but the searches continue. Data keeps coming in. Analysis techniques improve. And it's possible that someday something will show up. Some pattern, some feature, some anomaly that can't be explained by simple single universe models but makes sense in a multiverse context. Or nothing will show up, and the lack of signal will itself be information, will constrain the possibilities, will push us toward different models. Either way, we learn. Either way, we make progress. Let that two-sided progress be recognized. Theoretical work continues too. Researchers are trying to solve the measure problem, trying to find principles that uniquely determine how to assign probabilities in eternal inflation, trying to make predictions more definite. This is difficult work, technical, mathematical, but progress is being made. New approaches are being explored, new insights are emerging. It's possible that the measure problem will be solved, that we'll find a natural, compelling way to define probabilities in an infinite multiverse, and that would make eternal inflation much more predictive, much more scientifically robust. Or it's possible that the problem is unsolvable, that there's no unique measure, that eternal inflation is inherently ambiguous in its predictions, and that would be important information too. Would tell us something about the limits of the framework. We don't know yet which it will be, but the investigation continues. Let it continue without impatience. In string theory, researchers are exploring the landscape, trying to understand its structure, trying to find patterns, trying to determine whether some vacua are more natural or more likely than others. They're also exploring alternatives to the landscape, other ways the theory might work, other mechanisms that might select a unique vacuum rather than allowing so many. And they're working on connecting string theory to observations, on finding signatures that might show up in particle physics, in cosmology, in gravitational waves, on making the theory testable, even if only indirectly. This work is ongoing. It's decades into a long research program, and it's not clear where it will lead. Whether string theory will be confirmed, whether the landscape will prove to be real, whether multiverse scenarios will gain support or lose it. But the work continues, the questions are pursued, the mathematics is explored, and we wait to see what emerges. Let the waiting be patient. Breathe slowly. Let your thoughts drift. We've been talking about the future, about open questions and ongoing research, about possibilities that might be realized or might not, about observations that might clarify or might remain ambiguous. It's all uncertain, all contingent, all dependent on what we discover, what we measure, what we come to understand. And that uncertainty is okay. That's where we live, at the frontier of knowledge, where what we know shades into what we don't know, where theories extend beyond data, where possibilities multiply. Science is always in this state to some degree, always reaching beyond what's firmly established, always exploring, always asking questions whose answers are not yet clear. The multiverse is just a particularly dramatic example, a particularly vivid illustration of how far our theories can extend, how uncertain our conclusions can be, how much we still have to learn. But that's what makes it interesting, what makes it worth thinking about, what makes it a genuine frontier. Let the frontier be a place of rest rather than anxiety. There's something important to recognize, something about the relationship between knowing and not knowing, between certainty and uncertainty, between established facts and open questions. Absence of evidence is not evidence of absence. Just because we haven't detected other universes doesn't mean they don't exist. Just because we can't test multiverse theories directly doesn't mean they're wrong. But absence of evidence is also not evidence of presence. Just because multiverse theories are mathematically consistent and motivated by successful frameworks doesn't mean they're true. Just because we can imagine other universes doesn't mean they're out there. We're in a state of genuine uncertainty, not knowing, not able to know, at least not yet. And that's an honest place to be. It's tempting to want resolution, to want to know definitively whether the multiverse is real or not. But resolution might not be available. We might have to live with uncertainty, perhaps indefinitely, and that's okay. Uncertainty is not failure. It's not ignorance in a blameworthy sense. It's an honest recognition of the limits of our knowledge, of the complexity of reality, of the difficulty of the questions we're asking. Let that be enough. Many of the deepest questions in physics remain unanswered. Why is there something rather than nothing? Why do the laws of physics take the form they do? Why are the constants what they are? What is the ultimate nature of space-time, of matter, of reality itself? The multiverse addresses some of these questions in its way, or at least reframes them, but it doesn't answer all of them. It doesn't explain why there's a multiverse if there is one. Doesn't explain why the landscape has the structure it does. Doesn't explain why quantum mechanics is the way it is. It shifts the questions, transforms them, but doesn't eliminate them. And maybe that's all we can ever do. Maybe every explanation rests on something unexplained. Maybe there's no final answer, no ultimate foundation, just layers of understanding, each resting on something deeper, receding infinitely. Or maybe there is a final answer. Maybe there's a theory of everything. Maybe we'll someday understand why reality has the structure it has, why these laws and not others, why anything exists at all, we don't know. Both possibilities remain open. Let both possibilities coexist peacefully. The multiverse might be real, or it might not be. That's the honest assessment. That's where physics stands today. We have theoretical reasons to take the idea seriously. We have methodological reasons to be skeptical. We have no definitive evidence one way or the other. And that's okay. That's the nature of frontier science. The nature of the deepest questions. They don't have easy answers. They don't resolve quickly. They require patience, persistence, willingness to live with uncertainty. Scientists working on these questions accept this. They know they might not see resolution in their lifetimes. They know they're asking questions that might take generations to answer, or might never be answered definitively, but they pursue them anyway, because the questions are interesting, because the pursuit itself is valuable, because understanding, even partial understanding, even uncertain understanding is worth having. Let that value be appreciated. Future generations will know more than we do. They'll have better instruments, more data, deeper theories. They'll see things we can't see, understand things we don't understand, answer questions we can't answer, and they'll have new questions, new uncertainties, new frontiers, because that's how knowledge works. Every answer opens new questions. Every solution reveals new problems. The edge of understanding keeps moving, but it never disappears. The multiverse question might be resolved for them, or it might not. It might remain uncertain even centuries from now, or it might be superseded by entirely different frameworks, by ideas we haven't imagined yet. We don't know what the future holds. We can't predict how understanding will develop. We can only do our part, ask our questions, pursue our investigations, pass on what we've learned to those who come after. Let that be enough. Let the work continue across generations, patient and unhurried. Breathe deeply. Let the open questions rest. We've walked through the uncertainties now, the things we don't know, the questions that remain unanswered, the observations that might come, the theories that might develop, the understanding that might deepen or might not. It's a lot of uncertainty, a lot of not knowing, but there's peace in it. Peace in recognizing that we're in the middle of a long story, that we don't have all the answers, that we might never have all the answers, and that's okay. Science continues, research progresses, questions are pursued, even without definitive answers, even in the face of deep uncertainty, and that's valuable, that's meaningful, that's enough. Let it be enough for tonight. We're approaching the end now. Approaching the place where we return to the question we started with, the question that has drifted through all of these sections, all of these ideas, all of these uncertainties. Does the multiverse really exist? Let's come back to that question gently, without rushing toward an answer, without claiming certainty we don't have. Let's sit with it for a while. Let's see what we can say honestly about where we are. You can rest deeply now. The journey is nearly complete. The ideas have been laid out, the complexities explored, the uncertainties acknowledged. What remains is simply to gather them together, to see the whole picture, to find peace in not knowing. In strict scientific terms, the existence of a multiverse is currently undecidable. That's the clearest, most honest statement we can make. We have mathematically consistent models that include multiverses. We have mathematically consistent models that don't, and all of them, the multiverse models and the single universe models, are compatible with present observations. The data don't force us to accept a multiverse, but they don't force us to reject it either. Both possibilities remain open. This is genuine uncertainty, not the uncertainty of being confused or uninformed, but the uncertainty of being at the frontier, of asking questions that our current methods can't answer, of standing at the edge of what we can know. And there's a certain honesty in acknowledging this, in not claiming more than we can justify, in recognizing that some questions might not have answers yet, might not have answers for a long time. Let that honesty be peaceful. Within mainstream physics, multiverse scenarios are serious theoretical possibilities. They're not fringe ideas, they're not pseudoscience. They're explored by respected researchers, published in peer-reviewed journals, discussed at major conferences. But they're not confirmed empirical facts. That distinction is crucial. They're possibilities that arise from extrapolating successful theories, from following mathematics where it leads, from taking certain frameworks seriously and seeing what they imply. But implications are not confirmations. Possibilities are not actualities. The fact that a theory predicts something doesn't mean that something is real, especially when the prediction extends far beyond what we can observe. So multiverse scenarios have theoretical support, they have motivation from successful physics, but they don't have direct empirical confirmation. They're not established the way, say, the existence of atoms is established, or the expansion of the universe, or the existence of black holes. They're more speculative, more uncertain, more contingent on assumptions that haven't been tested. Let that distinction be clear. Many leading researchers treat multiverse ideas as testable in principle, but only through the parts of the underlying theories that are accessible to observation. Not through direct detection of other universes, that might be impossible, but through indirect constraints. If inflation is confirmed in more detail, if its parameters are measured more precisely, if certain models are ruled out or favoured, then that affects eternal inflation scenarios. It doesn't prove other bubbles exist, but it might make that possibility more or less plausible. If string theory makes predictions that turn out to be correct, if aspects of the theory are confirmed through particle physics or gravitational observations, then the landscape becomes more credible, not proven but more plausible. If decoherence is better understood, if the measurement problem finds a compelling resolution, if one interpretation of quantum mechanics emerges as clearly superior, then the quantum multiverse becomes more or less likely. These are indirect paths, circuitous routes, not direct observations, but gradual accumulations of evidence that constrain what's plausible. It's slow, it's uncertain, but it's how science often works when dealing with things we can't observe directly. Let that indirect approach be acceptable. The difference between using multiverse concepts as tools and asserting them as facts is important. Some physicists use multiverse ideas to think about problems, to frame questions, to explore possibilities, without necessarily committing to the reality of other universes, for instance. Anthropic reasoning can be useful even if you're not sure a multiverse exists. It helps you think about selection effects, about what kinds of universes could support observers, about why we might see the constants we do. Similarly, eternal inflation can be a useful framework for thinking about the early universe, for exploring the consequences of certain field dynamics, for understanding how inflation might end in different ways in different places. Using these ideas as conceptual tools doesn't require believing they're literally true. It just requires finding them useful, illuminating, productive for thinking through problems. And many physicists work this way. They explore multiverse scenarios without necessarily endorsing them. They investigate the implications without claiming certainty about the reality. This is a humble, pragmatic approach, one that recognizes the value of ideas without overcommitting to them. Let that pragmatism be part of how we understand what physicists are doing. The philosophical debates about the multiverse are active and unresolved. They reflect deeper questions about what counts as explanation, what counts as evidence, what makes a theory scientific. And those deeper questions don't have universally accepted answers. Different philosophical traditions give different responses. Different scientists have different intuitions. Different standards of evidence and explanation are applied. So the multiverse debate is not just about physics. It's about methodology, about epistemology, about the nature and limits of scientific knowledge. And those debates are valuable. They force us to think carefully about what we're doing, what we're claiming, what justifies our claims. They make science more self-aware, more reflective, more careful about its boundaries and assumptions. The debates won't be resolved quickly. Maybe they won't be resolved at all. Maybe they're the kind of questions that every generation has to grapple with anew, that don't have final answers but require ongoing engagement. And that's okay. The debate itself is valuable. The questioning itself is important. Let the ongoing nature of the debate be part of the landscape. Breathe slowly. Let your body sink deeper into rest. We've come to the end of the journey now. We've walked through cosmic bubbles and quantum branches, through string, landscapes and anthropic arguments, through philosophical debates and empirical challenges, through what we know and what we don't know, through certainty and uncertainty, through established facts and speculative possibilities. And we've arrived here at this question. Does the multiverse really exist? And the answer, the honest answer, is that we don't know. We have reasons to take the idea seriously. We have reasons to be skeptical. We have no definitive evidence one way or the other. The multiverse might be real. It might be a vast structure of which our observable universe is just one tiny part. Or it might be an artifact of our theories, a mathematical possibility that doesn't correspond to physical reality, a way of thinking that turns out to be misleading. Both possibilities remain open. Let them both exist, peacefully, without needing to choose between them. There's something valuable in living with uncertainty, in not knowing, in being comfortable with questions that don't have answers yet. Perhaps questions that will never have answers. Our culture often pushes us toward certainty, toward having opinions, toward taking positions, toward knowing or claiming to know what's true. But sometimes the honest position is uncertainty. The honest response is, I don't know. The honest acknowledgement is that the question is open, that the evidence is insufficient, that we're still learning. And that's okay. That's not weakness. It's not failure. It's honesty. It's humility. It's an accurate reflection of where we are. Science, at its best, embraces this, embraces uncertainty, acknowledges the limits of knowledge, remains open to multiple possibilities, pursues questions even when answers are elusive. Let that embrace of uncertainty be calming. The multiverse is an example of how far human thought can reach, how far we can extend our understanding, our theories, our imagination, from direct observation to mathematical extrapolation, from what we can see to what we can barely conceive. It's a testament to human creativity, human curiosity, human persistence in asking questions, even questions that might not have answers, even questions that might be permanently beyond our reach. We are small creatures on a small planet in a vast cosmos, and yet we ask questions about the nature of reality itself, about what exists beyond what we can see, about the ultimate structure of the universe or universes. That's remarkable. That's worth celebrating, even when we don't have answers, even when we're uncertain, even when we might be wrong. The asking itself is valuable. The reaching itself is meaningful. Let that be appreciated. Tonight you've listened to a question without an answer. You've walked through ideas that might be true or might not be. You've encountered uncertainty at every turn, ambiguity, incompleteness, open questions. And that's exactly what was offered. Not certainty, not resolution, not a definitive answer, just an honest exploration of where we are, of what we know and what we don't know, of what the theories suggest and what the evidence supports. The multiverse might be real. The multiverse might not be real. And either way, you've spent this time thinking about it, resting with it, letting the ideas drift through your mind like clouds, like shadows, like distant possibilities, and that's enough. That's all it needs to be. Let it be enough. The universe we can see is vast, unimaginably vast. Billions of galaxies, trillions of stars, countless planets, structures extending across billions of light years, a history stretching back nearly 14 billion years. That's enough to contemplate, enough to wonder about, enough to fill a lifetime of curiosity and investigation. Whether there's more beyond, other regions, other bubbles, other branches, other universes, is a question for another day. A question that might be answered eventually, or might remain forever open. Tonight, you can rest in what we know, in the vastness we can see, in the beauty of the observable universe, in the mystery that remains, whether or not there are multiverses beyond. There's enough wonder here, enough to sustain you, enough to inspire awe. Let that be where you rest. The night is quiet around you. The stars, whatever their ultimate context, are still shining. The cosmos, whatever its full extent, is still here, still mysterious, still vast, still beautiful. And you are here too, in this moment, in this universe, part of this extraordinary reality, connected to everything around you, to the atoms in your body that were forged in ancient stars, to the light reaching your eyes from distant galaxies, to the fundamental fields and particles that make up everything that exists. Whether there are other universes or not doesn't change that, doesn't diminish it, doesn't make your existence less real or less meaningful. You are here. That's certain, that's undeniable, and that's enough. Let that certainty be grounding. The multiverse is a question, one among many questions. one among countless mysteries. It's interesting, compelling, worth thinking about, worth exploring scientifically. But it's not the only question, not the most important question, not the question that needs to be answered for life to be meaningful or for wonder to be present. The universe we inhabit, the one we can see and measure and explore, is already extraordinary, already beyond full comprehension, already filled with mysteries and beauties and structures we're only beginning to understand, and that's enough, that's more than enough. Whether reality extends beyond into other universes is fascinating, but it's not necessary. What we have here, what we can see and know and experience, is already more than we can fully grasp. Let that sufficiency be peaceful. So does the multiverse really exist? We don't know. We might never know. And that's okay. The question has led us on a journey through physics and philosophy, through certainty and uncertainty, through what we know and what we imagine, and the journey itself has been valuable. The thinking itself has been worthwhile, even without an answer, even without resolution, even with the question remaining open. That's how some questions are. They don't resolve, they don't close. They remain open invitations to think, to wonder, to explore, to remain curious. The multiverse is one of those questions, and it can remain a question, can remain open, can remain uncertain, and you can rest in that uncertainty, can let it be okay, can allow the not knowing to be peaceful rather than unsettling. Let the question rest now. Let it dissolve into the stillness of the night. Breathe deeply. One last time. Let everything we've discussed drift away. Let it dissolve into the background. Let it become part of the quiet darkness around you. The multiverse, the theories, the observations, the debates, the uncertainties, all of it can fade now, can become distant, can release its hold on your attention. You don't need to remember any of this. You don't need to have learned anything. You don't need to hold on to these ideas. They were just companions for tonight. Just thoughts to drift through. Just patterns in the darkness. And now they can fade, and you can rest. Fully. Completely. Without questions. Without seeking answers. Just rest. Just breathe. Just be. The night is here. The silence is here. And that's all there is. All there needs to be. Let go. Let everything dissolve. Let sleep come gently, if it comes. There's nothing more to know, nothing more to understand, nothing more to figure out. Just rest now. Just rest.